so then we could go through area. I have some of the notes for it. Let me see. Is A stands for atom. Let's see if I can find it. Okay. And you use this when your charge is on different atoms. So we won't be using that one. But usually the larger atom is more stable. Okay, but our charge is on the same atom. They're both on the oxygen. So it won't be that one. R is for resonance. So that's when charge is on the same atom. And more resonance structures. Oh, whoops. Is more stable. And the only one we really use otherwise is I for induction, which is when the charge is on same atom. But oh my God, sorry, I'm running out of room. But more induction is more stable. Okay. So we're looking at the bases, and then could someone say like how we know, I don't know, what is induction or whatever?
That's based off of electronegativity, right?
Yes, yeah.
So wouldn't the conjugate base have the advantage since fluorine is way more electronegative than hydrogen?
Yes, yeah. So this one has more induction because it's more electronegative. So yeah, so that one has higher induction. So that means that the charge is dispersed. And it's more stable. So since the base is more stable, then that means that the parent acid is stronger. So then this one is stronger acid. And then this one's weaker. So equilibrium favors the weaker acid. So we'll redraw the equilibrium like that. Okay. Is that cool? Okay. Cool. Okay. So that's that one. This one is resonance structures, and I hate resonance structures. So we will see. First, I'll go ahead and redraw it.
What about question 3? Is not included in the exam?
No, it is not. I guess I'm not even sure what this. Oh,
Thank you.
I don't know what that would be. Yeah. Okay. Okay. So then, okay. This negative charge means there's extra electrons, I believe. So I'm thinking this, wait, is this equivalent to like two lone pairs right there?
Yeah, it is. I posted I guess what I think is the solution in Discord and the
Oh, okay.
answers and questions.
Cool. Yeah.
But
cool.
honestly, I'm not too sure because resonance is hard for me too.
I know, right? I feel like I was able to do it before. Okay. I have yours too. Okay, cool. So yes. Let me just move this down. And then I pulled it up last time we met, but rules for resonance structures, it's like you can go from lone pair to double bond, right? And also like double bond to like an adjacent double bond. And there's also one more, but I'm not too sure right now.
Said pi bond to pi bond, if I remember correctly.
Is that what? I think that's the same thing as this one. Double bond, pi bond.
Oh yeah, you're right. Sorry.
Okay, no, that's cool, but it is a pi bond. Cool.
Then that would be pi bond to lone pair because I looked up something.
Oh yeah, true. And vice versa, yeah. Okay, so these are all the things you could do to make resonance structures. So let's see if we can apply it. Okay. So for the first one, I'm kind of thinking I would do this first. And then just move this one over because you have to move like two at a time usually, right? Okay. So that structure. Would look like that. So I'm sure that's a resonance structure, right?
Yeah.
Okay, so there's that. Let's see. I wish we had an answer key because I feel like I'm gonna end up going overboard. Well, where else would you guys kind of want to move it? We went over it in office hours and she said there was only one resonance structure. Is that what she said?
Yeah, she said the pi bond towards the left, it's too far away.
Oh, okay. Okay. So then I feel like because I saw this like last time we were going over it, you could do a pi bond to another pi bond, which I thought meant like you could just go right here. That's a lie.
They'd have to be conjugated. Remember, like the isolated and conjugated double bond.
Oh,
Also, that carbon has 2 hydrogens, so now it would have 5 bonds. Another thing, like your hydrogens aren't going to move.
Yeah. Sure. Okay, cool. Oh yeah. Makes
Wait,
sense.
so that one you drew is the only one?
That is what everyone was told, and then let me see. And then I do see in yours,
So you can't go to the left, like if you start with it at the beginning.
yeah, I was thinking that. If instead we moved over this way, we still have 2 hydrogens here, so you wouldn't be able to do it here, else it'll have 5 bonds. That is very true. So it's just because this one's connected to one with a bond that can move over. That's why we go the other way. So that makes sense why it can't go that way. So it would be helpful maybe to just draw the hydrogens very small wherever they are. so that you don't end up with too many pairs. What were you gonna say?
So then it's like basically saying you can only move to a spot that has one hydrogen available. All right.
One
Or
or
no.
less, I guess. Yeah, I
Yeah.
think that's right. Yes.
Okay.
Cool. Okay. I'm scared to write that out, so I guess I'll just leave it. Okay, so just this one. Okay. Is that cool for everyone? Any other things you think might work? And then we said this one doesn't work, like to go to another double bond because we have the hydrogens right there. Yeah, so it makes sense. Okay. So there's that one. So we could go on to 6 then. Okay. So this one, draw an energy diagram and label which conformation is anti and which is syn. So does anyone remember what anti means or syn?
I know anti is when they're both on the complete opposite side of each other, but syn, I don't remember what that is.
Syn's the opposite, so it's like the closest one.
Okay.
Yeah, cool. Okay, so the ones that are furthest apart is going to be A, because these are our largest groups. And then syn addition is the opposite, where they're like as close as possible. So these ones are supposed to be on top of each other here. So there's that. And then also, so then how stable is this one? The anti-addition one?
The most stable.
Yeah. So then we know that the syn addition one is the least stable. And then in terms of the energy diagram, then the least stable one, does it have, okay, yeah, you guys know. It has the most energy. It's like about to react with everything. So it has the most potential energy, so that's a D. I'll put it all the way at the top immediately. And then for A was anti, it's kind of already there from last time, which was the least stable, or sorry, most stable, so least energy. Okay, and then otherwise, we go back up here and label them. Let me see, so I don't have the notes in front of me. So what's it called when they're on top of each other?
Eclipsed.
Okay, cool. Eclipse.
Other one's staggered.
Cool. I don't know if I'm spelling words right, but that's fine. This one's also staggered. And then this one is eclipsed. And then for stability with those, what's like the rule?
Usually eclipsed have more energy and staggered has less.
Okay. Yeah.
And of course, the farther or the closer they are determines like their general energy in their own category.
Exactly. Cool. Okay. Let's say more stable. Okay. Cool. So then we can compare all of these ones. So eclipsed, I'm just going to circle the higher priority groups that we're looking at. These. Okay. So it would be best to see the difference between our two staggered ones. So in both of these, they're just like right next to each other, but staggered. So these will have the same energy. Okay. But they will have less energy than the eclipsed ones. So that's C and E. And then for the eclipsed ones, we have one on this side. And then also here, let's see, like, which ones do you think are closer together between the eclipsed ones?
B.
That's true, because it looks that way, except it was a trick question because eclipse means that they're actually like truly just on top of each other. So either way, these two are like right next to each other right here. And then these ones are also right on top of each other. And they're right next to each other, just on the other side.
Okay.
Sorry. Okay, so both of those have the same energy also. Okay, and they just have more energy than the staggered ones, so we'll just put them a little bit higher. So, and there. Okay, cool. So, is that cool with everyone? Okay. So that's 6. Okay, and 7. Okay. So this one is 8. But
For
then
the last one, we supposed to do the line, like going like up and down, or you just leave it like that?
what do you mean the line going up and down?
Like I remember in the examples that were like they
You
do
kind of
like
have
the
to connect
graph,
them.
yeah, connect them, yeah.
Oh, you do?
Going
Oh,
up,
I
yeah, I
didn't.
have.
Okay. How am I supposed to connect them?
It's like a dashed line.
Yeah, like
between
a
the two to
dash,
show
Oh, okay.
equilibrium.
Oh, I thought that was just okay for looks. Cool. Okay, that's just to show the ones of same energy, right?
Yeah, exactly like that.
Okay, cool. So yes, also put in the lines. Okay. Cool. There's that. Okay, now we could go back to 8. So rank them in order of increasing boiling point. So like what characteristic determines boiling point that we keep hearing about?
This is where that like dissolves like thing comes in, right?
Yeah, so like dissolves like. And also that's referring to hydrogen bonding. So OH, just so we all kind of know, is a hydrogen bond acceptor and donator or donor. And then more hydrogen bonding means stronger intermolecular force, because it is like the strongest covalent bond or whatever it is, or it's not a covalent one, whichever one it is. So yes, so if you know that hydrogen bonding means that they're like stuck together more, that means it's going to take more heat to break them apart. So also higher boiling point for more hydrogen bonding. Okay. So for these ones, you would look at basically all the oxygens and hydrogens. Also hydrogen bond acceptors. I know it's oxygen, nitrogen, and then there's also some other ones. If anyone knows them, just for fun.
Is it fluorine? NOF?
I think it is also that.
Yeah.
And I think there's one more maybe, but who knows?
I thought it was just those 3.
Oh, okay, cool. Well, yeah. So all of those are acceptors. So when
Would
you see
be
this,
bromine not count since hydrobromic acid exists?
I'm not too sure if that is one.
I don't really know either. I was just
That's okay. Who knows? Possibly, but I think not. It's just like random though. So we can look at this one. This is a hydrogen bond acceptor. This is both the donor and acceptor. And then this one, donor and acceptor. And then this one's an acceptor. Oh, and also just another rule for it. I don't think it will, you know, it probably will never come up, but they have to have available lone pairs to be acceptors. But yeah. So
I just have a quick question. What would just a donor look like? Is that even possible?
just a donor.
Am I just thinking of something weird?
Oh, actually, I think it would be like just if you had like something that had all of these filled. Otherwise, then this one,
Oh, I see. Okay. Thank
because
you.
it doesn't have any lone pairs. Yeah, but will probably never happen. And yes, those would all also be donors in the chat, NH and FH. So let's see. So which one of these would have the highest boiling point?
A.
Okay, yeah. Okay, and then we'll just kind of go down the line. Yeah, so then D will have the second, then B, and C has the least. And just because it's slightly related and I always forget, otherwise for boiling point, more branching means higher or lower boiling point?
Higher.
Higher.
Okay. Cool. Okay. That's also a rule, but yeah, hydrogen bonding is, I think, stronger than that.
So if we get the test and there's no like acceptors or donors, we should just focus on branching, yeah.
Yes, yeah, we've had to do it
Okay.
before.
Or maybe just by like order of like IMF bonding, because that's like what kind of surpasses everything.
Yeah, exactly. So yeah, if there's any hydrogen bonding, it's more important than the branching.
What do you guys know? What happen to know what chapter the IMF is on?
Yeah, it's actually on page 3-13.
Okay, thank you.
Yeah, I'm gonna try to keep track of like what pages they're on, because this test kind of goes in order of like increasing chapters. So I'll drop it later.
Okay. And then someone in the chat, and I feel like I kind of also remember that, says they have down that more branching means lower boiling point and a longer carbon chain is higher boiling point. Does anyone know for sure and can confirm or
I
deny?
can confirm the carbon chain one. I don't know about the former statement.
Okay.
Yeah, I think like on 3.9, I have it noted about the carbon chaining boiling points.
Okay. So longer. I think that they are inversely related. Lupita, are you saying that on that page it has it straight up?
Yeah, I can confirm it in the notes. It's on page 3-13 and 3-14.
Okay, cool. Okay, so then more branching is a lower boiling point. But that's okay, just so we know.
So what's branching? Like the amount of places that hydrogen bonding can happen, or?
Branching is like this. So like
Oh.
basically when there's what else is that called? I don't know. You know.
Yeah.
Yes, branching. Okay. Okay. Cool. So that's 8. More surface area has higher boiling point? Question mark. Yes, yeah, that's true. Because longer carbon chains have more surface area. So that's, I remember that being explained at some point.
Yeah, that's on 3.13 also, right above like the blue. I don't know if you're looking at it, but above the blue note that's on the notes.
Not me specifically, but yes. Yeah. And then I'll post the this in the chat also when we're done. So yeah. Okay. So that is 8. Next, we can go to 9. So for this one, add the substituents to the chair confirmation to complete the chair flip. So, can anyone like name some of the rules for chair flips?
Up stays up, down stays down.
Yes. Okay. And then also the numbering maintains like the direction. And then, oh, and then another thing that was pointed out at one point, just for fun, was that larger groups prefer equatorial.
Is ET Ethel?
Yes,
For sure.
I always forget. Oh, and then on that note, I knew I was missing something. And also that's gonna be equatorial turns into oh god, what's the name for the straight up or down one?
The axial? Yeah.
Yes. Okay. So those are like all of the rules for the chair flips, basically. So first I'll renumber it going the same way. This one's going clockwise, so I'll go clockwise again. So 2, 4, 6. Okay. And then they're going to be on the same carbons. So for ethyl, it's going to stay up, but it will turn into an equatorial position. So T, and then PR, whatever that is going to stay down, but turn into the axial position.
I think it's propyl.
Oh, yes, yes. Okay, cool. Cool. Okay, and then redraw the equilibrium arrow to indicate which will predominate. So that's where that later rule comes in. Larger groups prefer equatorial. So which one's gonna be, what's the
You know,
word? What was that?
wouldn't it be B, the predominant?
No, because ethyl is the 2, and then propyl is the 3. Oh, that's not 3. Whoa, wait, whoa. Why am I having a stroke? This is besides the point, because I still know that this one's larger. This is propyl. CH3, CH2. No, that's
No,
beautiful.
Yeah,
Okay.
ethyl would just be a line.
Yes, there we
basically.
go. Okay, cool. Yes, anyway, so propyl is our larger one, and it prefers equatorial, which is like the one coming out of the side. So it'll be more towards A than B. That cool? And then yeah, I'll just note this is axial. And this is equatorial. Okay, cool. So there's that one. We could go on to the next one then. So this is Determine if it's going to go SN1, SN2, E1, or E2. So I'll probably be switching between my notes on these because that's what I'll be using for the exam. So let's see. OH minus is a base or a strong base. Actually, here, wait. First thing we should do
That's a strong base, right?
is go through. Yeah.
So that'll be E2 most likely.
Let's see. So it's a good leaving group, and then tertiary carbon. Yeah. So then it should be E2. I think. Can I confirm that? And then, does this one count as a nucleophile also? Can anyone say?
I believe so. It would be a
Okay.
strong, I still think a strong nucleophile.
Yeah, that's what I would think. Okay. And then let me go ahead. I'll just get my other notes.
But an SN2 can't do a tertiary, so
Okay, yeah.
you can rule it out by like that way.
Yeah. This is still the wrong one. This- Okay. So we can switch between these two. So yeah, tertiary only E2, no SN2. It's too crowded. So we'll switch back and forth between this. We'll go through it. Okay. So yeah, so that one's E2. We can just say that because it's a strong base, and no SN2 with tertiary carbon. So yeah. Otherwise, just so you don't like mess yourself up or anything or get too ahead of yourself, this is like a poor leaving group. We can say this one's also a poor leaving group. And this is a good leaving group. And then for C, just since we see it already, fluorine is so poor, it can't even be turned into a good one, so it'll just be no reaction. So there's that. And then for this one, I'm just gonna change the name because we know ET was ethyl, so that's CH3CH2 OH. Okay, so we have that one. We also have this one for B. H2SO4 and heat is a good question. I'm not too sure. I know that's a different reaction. Let's at least look at what that is.
A rule of thumb,
H2SO4 and heat. Oh,
I was gonna say a rule of thumb that got me the answer right on the last test that we had was that if you have H2SO4 and heat, it's gonna be elimination. But if it's a tertiary or a secondary, it's E1. And if it's a primary, it's E2.
wait, okay. Okay, hold on.
Very
Sorry.
helpful.
And you said if it's a primary or secondary?
No, if it's just a primary, then it'll be E2.
Okay.
And if it's secondary and tertiary, it's E1.
Okay. Cool. Awesome. Okay. And then H2SO4 and heat is just basically for alcohol, right?
I've only
Otherwise-
seen alcohol, so
Yeah. And then otherwise, I think H2SO4 is a weak anything, right? Nucleophile or base.
I don't know. I didn't.
I feel like I've seen that by itself before. If anyone can confirm.
Yeah,
or
it's a
deny.
strong acid, but a weak
Yeah.
nucleophile.
Cool. Cool. Okay, yeah. So if you see H2SO4 by itself, it's weak. But with heat and with an OH group, it does that one reaction. I'll go back to it in a second, but otherwise, this is a secondary carbon, and this is a great little thing here. So it's gonna go through E1. And we'll go back to this one. Yeah, for secondary, it could have done it either, but oh yeah, and we already said it's a weak base or nucleophile. So yeah. And this is another useful thing because it comes up a lot. Okay. So that so we know. Cool. Okay. So now we could go down to D. And then we know it's a good leaving group. This is a tertiary carbon. And this ethanol is going to be a weak weak nucleophile specifically, I think. But I mean, usually it's just also a weak base. I'm scared to say it right now though. I'll just leave that. It's a weak nucleophile. And then also I've noticed when determining, have we had any strong anything? Yeah, I guess so. Well, it would be easier if we had a what's an example of a strong base? Anyone? Oh my god, what is it?
Sodium
NaOH.
hydroxide.
Yes, cool.
Yeah.
Okay, cool. Exactly. So when determining if it's a weak nucleophile or a strong nucleophile, or weak base or strong base, ionic bonds are usually like signals of a strong nucleophile or base. I'm just gonna say like usually strong nucleophile or base because I'm scared to commit to that. But from everything I've seen, yeah, that's how you determine. So yeah, this one, like this is charged, but it doesn't have another species that's charged. So it's a weak nucleophile. So anyway, a weak nucleophile on a tertiary carbon, I think is SN1, but I want to double check and make sure that that works. Yes, so SN1 does occur on tertiary carbons. Okay, is that cool for everyone?
Yep.
Cool. Okay, cool. There's that. I could go to 11. So determine the maximum number of stereoisomers based on the structure below. So does anyone remember the like equation for that?
2 to the n, right?
Yeah,
Was that, or was it
yeah.
reversed? Okay.
No, that's it. N is the number of chiral centers. Okay. And then also just to get it out of the way, so chiral center means that there are 4 different like attachments, I'll just say, on one carbon. Okay. So yeah, I'll just go ahead and do it then. So all these also are going to have like a hydrogen. So here on this carbon, central carbon, we have a fluorine, we have a hydrogen, we have like basically all of this or whatever. And then on this side we have this. So those are all different. So that's a chiral center. This carbon, it has a hydrogen also, and it has this, and it has like this, it has this, which are all different. So that's also a chiral center. I'm just gonna go back up for the person in the chat. So yeah, secondary and tertiary with H2SO4 and heat are E1 reactions. for this carbon, just to go in order, it's attached to 2 hydrogens. So these are both the same, so it's not chiral right there. Or well, that's not a chiral center. This one is attached to a hydrogen, different. This is different than this. They're all different. So chiral center here. This isn't a chiral center. This one is going to be a chiral center. This one also is going to be chiral center.
So it's not necessarily what it's directly connected to, but rather like the sections that they're connected to.
Yeah, it's kind of easy to just do that sometimes, because yeah, if you're not seeing anything different, where was it? So like for the BR one, when you're comparing, you have like this BR and this hydrogen, but like these two are the same. So then you end up going to the next one, and then those technically are the same. So then you go over here and here, or maybe here. But yeah, you'll just be able to tell. So that's why sometimes I just do the whole section. So it'll go off that way. And then this carbon is not a chiral center because it's attached to 2 of these same things. So I think that's all of them. So that's 1, 2, 3, 4, 5 chiral centers. 2 to the 5th is a number. I have a calculator. Okay, so there's 5 chiral centers, so 2 to the 5th is 32 stereoisomers. Okay, is that cool? Okay. Yeah. Okay, so we can go to 12. Circle which is the more stable alkene and state the differentiating factors. So there's just like, I think just one rule about alkene stability, if anyone remembers what makes it more or less stable. And we kind of heard about it with the elimination reactions.
Is this determined by how substituted the pi bond is?
Yes, yeah. So more substituted is more stable. Okay. Yeah, so this one's just asking which is more stable. So we'll check how substituted each of them are. So this one is tri-substituted. And this one, oh, whoops, don't do that. This one's just di-substituted. Cool, yeah. Someone in the chat said too. Cool. So the more substituted one is more stable. So that one's tri-substituted. And then, is everyone good with like knowing basically where to put these dots? Because I know back during one of the other ones, it was kind of hard, I heard, for some people. Because you definitely don't like start here, just whatever's connected. So yeah, that's the difference between figuring out substitution in degrees. I feel like I don't know how exactly to answer it because degrees, let's see. I mean, that kind of is the degrees of this one. Like, yeah, I'm pretty sure this one's like just 1 degree and then this one's 2. So it's tri-substituted in the end. So based on double bond. Yes. So substitution, it's just asking whatever is connected to the double bond, not including like this carbon that's already included in the double bond. Double bond is alkene being observed. Yeah.
I think the degrees are like when you're determining primary, secondary, or tertiary, it has to do with how many carbon bonds the carbon we're looking at has. Whereas whether it's substituted is how many R groups are attached to the carbons in the that have the pi share the pi bond. So like, yeah, like the degrees is how many carbon bonds attached to the carbon. They kind of sound the same, but like the R group, the R could kind of be anything, I think.
Yeah, they are like pretty similar. I mean, as long as you get both of them in their own right, pretty good. Cool. Okay. So then we could go on to the next one then. So explain why compound A has a lower pKa than compound B. First, we could just like notice what's the difference between these two.
Does it matter that it's aromatic, the benzene?
Yeah, it does, but right now I'm not remembering exactly what it is. How it affects the pKa, or
No,
sorry,
that's-
pKa. Okay, so I think that was told to me last time. So does anyone just remember how benzene rings relate with pKa or acidity? Oh, I think they're acidic, right?
Draw the conjugate base.
I can't. I'm scared. Okay. I don't know what to take from that. I think I understood it last time from that, but oh, thank you, Lupita. Okay. So does anyone like else see the difference here between the two? And then we know when we're determining like acid stuff, we could go by area. So the fact that it's a benzene ring, yes, it has more resonance. Resonance. Okay, cool. So has more resonance structures, which means the conjugate base is more stable, which means the parent acid is more acidic. So, dang it. And then pKa, I never remember. Lower means more acidic. Or what is it? Okay, lower pKa equals more acidic. Okay, so which one has the lower pKa is A. Is that cool? Makes sense. Explain again. How do you determine the pKa? That's just like a relationship that we know or are supposed to know, but I forget. So a lower pKa means that it's more acidic.
I have a question.
Mhm.
So like obviously we have to use like I don't know how to say it, ARIO. What's it called? But
Yeah.
would you have to go in that order, because on the O section on 5-13, and I guess like an easier way to look at it would be like, what's it called? S character. So it kind of like shows the bond, and it shows like triple bond, double bond, single bond, and in that decreasing order is the increasing of pKa. I hope I didn't tell you this. I'm sorry.
Yeah, I simply don't. I know I don't remember what the O is. So Morris character is what?
Oh, it said what's it called? More S character had more stability. And then it looks like the order of, obviously decreasing
Mhm.
bonds was, let's see, it looks like decreasing pKa also. Or let me make sure I'm saying that right. Hold on.
That's okay. Let me
I'll
see.
just type it in the chat if someone wants to verify it.
Okay, yeah. Or so then I remember that's like SP3, SP2, and SP.
Yeah,
Well, just
yeah.
SP.
It was like
So
that. And then for the SP3, that had like the highest order of pKa. And then
SP3. Oh, okay, yeah, that makes sense. Cool. Yes. So the S character is basically like determined by like the ratios. This is like 1 to 2, and yeah, I think so. And then this one's 1 to 3, and then this one's 1 to 1. So more S character means it's more stable, which means the parent acid is stronger. So yeah, that also are the compounds bases. The compounds were originally acids, but when you're trying to determine which is more acidic, you look for the conjugate base. Yeah, so that's what we did. So yeah, the orbital one also, like, it just confirms what we're talking about. I think O is more for acidity of terminal alkenes. Is that how that one was used specifically, or is it kind of for everything? I thought it was for multiple, but it definitely comes up for terminal alkenes because I mean, a terminal alkene wouldn't be the most acidic, and that's why they are acidic. Oh god, everything makes sense now. Thought it was based because of the OH has it an acid. I know, right? I think that's just because this is like, it doesn't say it's an acid, but this is the compound we're given, and then when it asks you to find which is more acidic, you just have to I think acid. Are we assuming, can someone confirm that this is an acid and then we just go with the conjugate base? Like, I don't know how to explain that a little bit better. Because if there is a hydrogen to lose, like, I don't know, I'm like, that's just what you do. I don't know if anyone else has a better explanation for the question in the chat.
Kind of. For these types of problems, I had one and then I lost it. Hold on. Anything can really act as an acid or a base. So like you can basically put anything and then make it either a conjugate acid or a base by either adding or taking away a hydrogen. But if you want to look at it a different way, the OH group is an alcohol, and I believe somewhere in like chapter 8 about alcohols, it says the alcohols are slightly acidic.
Yeah, I think that was said. Yes, and that is very true that it's like something is an acid or base like relative to like whatever it's reacting with. So you could interpret it as either, if we were given another one, I can't even think of one off the top of my head really, because like pKa's are all weird sometimes. But yeah, it's relative, yeah. So yeah, just remember to draw the conjugate base when determining the acidity, and then also put down here area. And then I think you are supposed to go, so I was saying, in order of like ARIO. But yeah, just resonance came up, but the O also confirms it. So yeah, is that one cool? Okay. This next one I kind of died on. Okay. So 14, just determining the relationships between the compounds. So let's see. just like if anyone can have some rule or like has any rules for these, I believe diastereomers, you need 2 chiral centers, right?
I believe so, yeah.
And constitutional isomers means that the attachments are different. And yeah, I think that's where I'll leave it for now, but also I don't know how to put it in, but switching from like R to S determines like, I guess if it's an enantiomer, so like for this first one, that's what we can do. So for this one, we also have a hydrogen in the back here. So when we're determining priority, we're gonna go 1, this one's 2, this one's 3, and then this is our 4th, but it's in the back, so it doesn't really matter. It's going this way, which is counterclockwise. So that's S. Then for this next one, 1, 2, 3, going this way, which is clockwise, which is R. So, oh, okay. So that's what I'm trying to say. So same compounds, they like maintain the same direction. I don't know if there's a better word or like one word that sums that up, but like R/S stays the same. And then for enantiomers, like, I guess I'll just say R will turn into S and vice versa. And then just like kind of remember, and I'll say, well, for diastereomers, only one will change. I guess I'll put it over here. Yeah, or the other way around. So those are some good rules to put down. So for this first one, we only had 1 chiral center, so it flipped. So 1 and 2 should be enantiomers. There's that one. We could go on to this next one. The first thing I'm gonna do, because it's a little bit easier, let's do the RNS. So 1, oh, nope. This one doesn't have, uh-oh, I think I went back too many times, yes. Okay. So, well, can you determine RNS for this one? And you can't, because then you would be like determining the priority groups, and these are the same. So there's no chiral center there. But let's see. So these can't be diastereomers. It looks like this one is rotated this way, so that it comes out over here. But honestly, from here, this is where it gets like a little bit too complex for my brain. Oh, actually, you know what? If you imagine it rotated, just like flip this like all the way around ish. 180? Yeah, that much. And then we have the same structure. Oh, actually, wait. Oh, we would actually have to flip the other one, I think. But I think they are the same structure. Let me double check. God, these ones get like very convoluted for me. Let me see. Okay, we'd move this one down, like rotate it. So instead it would be this way, and then back down.
It was the same compound.
Yes, except someone has a better way, I think, to explain. They're cis and trans, so that's great. I didn't know how to do that otherwise. So yeah. Let me put back here. No R or S. because they're the same. And then this one is going to be trans. And this one is going to be cis. Uh-oh. But then since they're cis and trans, she said they're diastereomers. Uh-oh. Okay. Yeah, I guess I just thought that diastereomers had to have 2 chiral centers. So I thought that that's just like a rotation that you could do. Did she say that they were diastereomers? Or does anyone else have any thoughts on that? I think I also have another thing in my notes. Actually, I have no idea where exactly it is. Let's see. Not there. Okay. In the notes it says easy isomers are diastereomers. Okay, cool. Okay. I don't even know where my thing went. Oh, no. Okay. Cool. So I guess so either 2 chiral centers, but I guess not always. I'll go down. In chapter 6, page 8, that says easy isomers. Uh-oh. Cool. Good to know. Okay, so 3 and 4 are diastereomers then. Okay. Cool.
So they don't need to have 2 chiral centers?
No, I guess not. I guess it's either way.
I
Let me
remember
see. So
diastereomers being like when there's like one of the wedged or bond thingamabobs or something, only one of them changed as opposed to both.
yeah, exactly. That's what I remember more, but let me see. So I think that's chapter 6. Yes. Okay, cool. Because up here it has like all of the rules. So okay, cool. So stereoisomers, let's see, in order, I guess. So they have the same molecular formula, and the same connectivity. Determine if there's a difference in spatial arrangement. So yes, that means at least they're stereoisomers. And then, okay, so spatial arrangement can mean RNS or E and Z. So I guess not specifically, but otherwise, if you don't have like a double bond, then it would have to have 2 chiral centers to be a diastereomer. Oh, okay, sorry. So if I kept reading, determine if the only difference in spatial arrangement is via alkene. And it was. So yeah, diastereomers. Otherwise, no. See, so this is kind of a good thing to have if you want. Yeah, that's also 6-8. Cool. So determine how many chiral centers. If there's only one, then it's an enantiomer. Diastereomers aren't possible with only one. So yeah. Oh my God, why would you say that, Lauren? I'm very scared now. Sorry, what was someone gonna say?
Literally.
I'm so scared now. I'm all alone. Okay. Yeah. Okay, I'm scared again. Okay, anyway. So the next one we could do 5 and 6. So here, first of all, I mean, do they have the same connectivity?
No.
Cool. Yeah, so 1, 2. And they don't have the same connectivity, so then they're constitutional isomers. Okay. Oh my God, and why is this? There. No. Okay, give me 1 second. And then, I don't know, maybe try and do the next one if you have it in front of you. Sorry, I got a phone call. Okay. Anyway, what does it mean having the same connectivity? That means that they are the substituents are connected on the same atoms. So for this one, yeah, like this would be 1 bromo, 3 methyl versus like 1 bromo, 2 methyl. Yeah. Okay. Cool. Yes. And then, sorry, I was saying that I hate this next one. But let's see if we can determine the rules. So, so I think it's that, correct me if I'm wrong, in the chair confirmation, like down, well, it basically equals dashed, and then up is a wedge. Is that true or false? She explained it in office hours. So then I guess, was that the reason that she gave, or what was the reason she gave?
Yeah, yes.
Oh, okay. So that's
So that's
okay.
the same compound.
Yeah. Yeah, it's just like rotated. Cool. This one just makes me wonder, I don't know if she happened to say it, but if this were like equatorial, what would I do? Or is it the same thing? It might be the same thing.
I think that's a difference between 2D and 3D. I don't think we have to worry about that for this problem.
Oh, I think that might be true. Okay, cool. Well, yeah. So yes,
But she did go over it though in the office hour. Somebody asked what if F was I believe equatorial.
Yeah, that's what I was saying.
And I think she said it would be diastereomers.
Oh. Oh,
and if it was the
makes
opposite, it would be enantiomers.
Okay, that makes sense, I guess, because then it would be like a line. I hate that. Okay, I guess. When here, wait, let me.
How do we know that it's a? How do we know like that the fluorine is like equatorial?
So hypothetically, I'm just trying to work it out. I think if it were equatorial, this would be the numbering for it, and then there's also a hydrogen here, but it's not 3D, so you couldn't determine R or S. That's what I was hoping to do, but I don't think you can. So I don't know. Solution, I don't know. But I mean, I guess you said if it were axial, if one of these were axial, I guess it would be a diastereomer. That's, I mean, because it changes R and S, but I just wish I knew how that kind of connected. But hopefully it'll be like this. If it's not like this, then maybe they're diastereomers. And if it's like straight up the opposite, like if it were like this, I think, then, oh God, I think that would actually just flip it upside down and also be right. I don't want to do the hypotheticals anymore. I don't know. I trust her. All we have is up means wedge and down is dash. So yeah, we'll just go with the same compound. So I don't know how to explain this one any further. But yeah. So yeah, that's all of those ends. Is that cool? Cool. All right. So let me see. So then we could go on to the next one. Oh, okay, and these are the rules. I just put them in before. Okay, so this one, predict the products. So yes. Oh my God, what is this first one?
Wait, what was the answer for the last one? For 7, 8?
Yeah, those ones are the same compound because when it's up in the chair conformation, that means it'll be a wedge. And if it's down, then it's dashed.
All right, thank
you. And then, so for this next one, I kind of don't want to look at this one right now. So I'm going to skip it for a second because the other ones are a little bit easier. So for this one, I mean, these ones are the bane of my existence, yes. But yeah, this one's a little easier. So this one's a strong, bulky base. And then this is a good leaving group and a tertiary carbon. So it's going to go through like E2, just so we know, or like elimination in general. Yeah. So for strong, bulky bases, though, they have a different rule. Does anyone remember the name of the rule?
Hoffman's? Yeah,
Right? Is it Hoffman's or yeah, Hoffman
that's Hoffman.
is the opposite one. Okay.
It's like Zaitsev or something.
Yeah, so Zaitsev is like the normal one. I'll just put it over here. So hydrogen. Wait, no, sorry. I was gonna do whatever that other rule is, but more substituted alkene. So that's like the usual rule for elimination reactions, but when it's a strong bulky base, then it goes by Hoffman's rule, just because it's like so dense already. I think that's why it's easier. So less subalkene. Okay. So we're gonna get rid of the leaving group, and then well, I guess our possible ones. So when you label it, that's your alpha carbon, and then any other carbons attached, except for what's it called? 4 degree. What is that? I don't know. Those ones can't this way. Like if this was your alpha over here, this one isn't considered a beta because there's no room for a double bond. But anyway, so the least substituted alkene would be this one. So move this over, and I'll copy the structure. Okay. And this one's only di-substituted. If we did this one, it would be tri-substituted, and this one's also tri-substituted. So there's that one. That was easier. So then we have this next one. Cl2, that's part of the alkene reactions. And then I'm gonna put the link for a Quizlet that I have. It has like all the alkene reactions, but it does not have like much of the later ones.
This one is halogenation.
What was that?
I believe this one is halogenation.
Oh, okay, yeah. I was
You
wondering
have
what
the
the
two
actual name.
chlorines. You have the two chlorines attached to the double bond. One is wedge, one is dash.
Yes, cool. Anti-addition.
Yeah, that was in the extra credit last test,
Oh, cool.
but it was with bromine.
Oh, yeah. Yes, I got scared of that one because I was trying to like rotate it or something weird. But you don't have to do that.
I ended up remembering that it was the same problem that we saw in the notes.
Oh, cool.
Page.
Yeah, true. Oh, okay, and then let me see. Wait a second. So yeah, halogenation replaces like each of these double bond parts with a chlorine in an anti-addition fashion. So yeah, one wedged and one dash. Cool. There's that one. This next one.
Sorry, can I see the answer? Just a second. Thank you. Thank you so much.
The enantiomer or like any sort of stereochemistry other than like the wedge and the dash for part C?
Oh, I hate those. Yeah, I always forget about those. No, I don't think that one has an enantiomer. Let me actually, I would think it would actually. Just kidding. I probably should.
It was in chapter 5 before we did that, but like I feel like it would make sense to have both, so I just wasn't sure.
Yeah, that makes sense. Okay. I was just trying to link my Quizlet. So that one has like at least all the alkene reactions on it if you guys want it. Dang, I don't have that part in my notes. I definitely think it would be. We can double check the chapter because that is important. If it has an enantiomer. Alkene reactions, that's chapter 5. Okay.
Yeah, chapter 5 was before we had done anything about chirality or like enantiomer and stuff, but like I wasn't sure because it seems like it would make sense to have one.
Yeah, I forgot these aren't my notes. Okay, let me see. Because I know also for like SN1, I think you get that naturally. Yeah. Dang. It doesn't necessarily say, I don't think. I don't know if anyone else happens to know. I literally think it does, but no, I'm scared.
Well, on exam 2, I believe, the one we took, I think question 8, number D, she wrote the enantiomer for it.
Oh, okay, cool. Yeah.
I don't know if we want to use that as a reference, but it's sort of similar, just not the same compound.
Yeah, so it was like also halogenation and
yeah, it was with bromine instead though. Yeah,
that's cool. Okay, so for her answer key she put plus enantiomer or whatever.
Yeah, she put both of them, but I don't know if this would work with plus enantiomer if you have to draw it, only because, well, no, I guess that would work actually, because those are the only 2 chiral centers. So
oh yeah, if you had too many that would get cray. Okay.
Yeah. Does the enantiomer have to be based on the chiral center?
Yeah, yes, because I think that's the only way you could get them, right? With
they have to be defined like with wedges and dashes in order to like know which is R and S and to determine if they're enantiomers.
Yeah, remember that.
Okay, thank you.
Dang. That reminded me, there's like a whole example about that I definitely forgot about. Where like, yeah, if the wedges and dashes aren't drawn, then you don't say plus enantiomer, right? Or, yeah, I guess if your answer just isn't wedged or dashed, you don't have to specify. That what it is, I think. Sorry, I let my thing
I know
come
when
out.
you're naming a compound, if wedges and dashes aren't defined, then you can't do RNS when naming. I'm really not sure about when we're drawing the compounds though. It's kind of got me twisted.
All right, that's okay. It'll be fine. Okay. Okay, anyway. So then for this next one, I don't think that it, yeah, I don't think there's any reaction with like nitrogen at all with that. But this one, what's the name for this? I forgot. What's the name for these reactions? These are
Wasn't it like esterification? I think that was like right after it.
Reduction
no.
of an amide.
Yeah, reduction. Yeah, so this one and this next one are both reduction reactions. And it's just helpful to know that it like basically turns into an OH because it's going to react. So let's see. For LiAlH4, that one is like the stronger of the two, just so that we remember. And it can react with, let's see, I'll put it over here. What is it? So it reduces ketones, aldehydes, and carboxylic acids. Oh. Okay. Okay, give me 1 second. And then the NaBH4 is just not going to do the carboxylic acids. Oh my god. All right, give me 1 second. Let's do it myself. Okay. Anyway. Okay, so for this first one, they reduce ketones and aldehydes into like OH groups. So we just go ahead and that's going to turn into an OH and H, and it doesn't react with the amide, or I don't even know the actual name for it. That's accurate. So we have that one. And then,
Wait, I think it's doing different for this reaction. Let me find it in the notes just so I can verify. But I think that this is one of the like carboxylic acid derivative reactions. So I think it's on like the end of chapter 14. Yeah, there's 2 reductions. The carboxylic acid derivatives that can be reduced are esters and amides, and this is an amide.
oh,
So the oxygen would just be replaced by 2 hydrogens.
Okay, I forgot this. Okay, yeah. So give me 1 second, and then I'll actually pull out those notes. So it's not just like a amide or amine, whatever. Yes, it's a carboxylic acid derivative. So let me find some notes on that. I have them all in here.
Yeah, I believe she's right. I think just she says to help visualize it, it's like the carbonyl just kind of goes away and it's just an amine, not an amide.
Oh God. Okay. Yeah, I don't even know. Okay, sorry. So you said what basically happens?
Like the carbonyl just goes away basically. So like it just like
I
she
wish
just
I knew.
in the note she just like she just says to visualize it, just scribble it out.
I'm like, which one is the carbonyl?
Like double bonded to oxygen.
Double bond. Okay.
So that just
Really?
goes away. And so you'll
Oh, okay.
have so that OH won't be there. Yeah, just it's just
Okay, cool.
yeah.
A double bond
Okay.
wasn't a ketone?
No, it's not the ketone. Yeah. So a ketone would be like if it were like way separated from this, like and nothing here, that would be a ketone.
Okay.
But since it's next to this, it's actually like this whole thing is a carboxylic acid derivative, including the OH. Okay,
Solid.
cool. Yeah. Okay, cool. So yeah, we'll just do that with this. Okay. Cool. Okay. I'll look at that more later too. Okay. So there's that one. Yes, then we can find it on 14, 12. Okay. So then for the next one, we have NaBH4. So can anyone just like say what's gonna happen?
The aldehyde will get reduced, but the carboxylic acid won't.
Yeah. Okay, cool. Okay. So yes, this one gets reduced. And we're just gonna keep like one of these OH. Okay. Okay. Kind of confused on D, so here, wait, give me a second. First, I'm gonna let my cat in. So we can check the notes for that one, or I don't think that these ones are, no, not helpful enough. So let me go back. Chapter 14, page 12. Okay, cool. So this is all reduction reactions, which is with Li and Na, all those. So we had an amide. So it says amides can be reduced to form a primary or secondary amine. And so, okay, and now I know what amide means. Amide is the carboxylic acid derivative. So that's any like double bond O attached to N and like literally anything with like a H or maybe no H, 2 H's, whatever. So yeah, so that's what an amide is. And it's reduced to form an amine. So yeah, you basically just break it off to form just like an H actually. Oh, okay, and then you keep the amount of H's that you have. So yeah, basically just cancels it out for amides. So yeah. Let's get into the other ones now. Okay, so there's D and E. Could go on to F. I have no idea what to do here really. I'm gonna go to the next one really quick because this one's a little bit easier. HBr. Let me double check my reaction thing. I'm having a stroke at the moment, but that's an alkene reaction. Yes. HBr is hydrohalogenation.
Okay, good to know.
Okay. And then for that one, that's also in the little notes that I sent. Hydrogen is added to one side, plus and whatever your X group is, because it could also be like Cl or what else? Let me see. Or I. Ugh. Okay. So let me see. Okay. So we have this alkene here. Oh, they're gonna stay the same. Okay. And sorry, so we also know, oh, whoops. Gonna go by Markovnikov addition. So hydrogen added to side with more hydrogens. Okay. So on this one, the side with more hydrogens is this side. So, or sorry, this side. And we'll add the Br to the other side. Okay. So there's that one. Now this last one is also an amide, which is a carboxylic acid derivative. So I'm going to go to these notes. I don't know if anyone just automatically knows which kind of reaction that is.
This one's the reaction with an alcohol. And so there's like in the little chart, it says there's no reaction for this one.
Wait, okay. Let me go back.
Just
so
that amides don't react with alcohols, if that is more clear.
Okay, yeah. Alcohol. Cool. I was just looking at this and only thinking like weak nucleophile or base, but it's an alcohol. And yeah, so you look for amide reactions with alcohol. I think I might have it hopefully a little bit nicer. Okay, wait. Not all of them. How sad. Okay, well now I know. Oh, or these are the only ones that actually react with alcohol. Yeah, but amides do not react. Okay. So yeah, I can also upload my little cheat sheet, but that's the one I'm turning in, so no one steal it. Yeah. So we skipped A earlier.
Chapter 14, page 7.
Cool, thank you. Let's see. 7. Okay. And this is, oh, okay, this is an ester. I'm not like retaining anything from these last ones. Okay, so chapter 14, page 7. Sorry, oh, cool. Yes, I forgot about these. So these are reactions with, wait, what kind of reactions? Sorry, hydrolysis, yeah. So we have an ester, and H2SO4 is just what we use for hydrolysis, the acidic version. So for that one, we're going to replace the OR group with an OH group, and then our OR over here will attach to one of the hydrogens from the H2O. Okay, so try it. Okay, is that right? I think I already messed it up, maybe. Let's see. Yeah, I'm gonna go really quick. So yes, we have our OR group. We keep our ketone, yes. We have that OH group. And I'm getting kind of tripped up on that other product. So it should be our, like, which are, well, I guess our group was just CH3, I think. Yes, we just have CH3 here. CH3OH then, I think. Yes, and I will send the notes in the Discord after. And then let me see, I can also do this. Can anyone confirm if I just did that right? Chapter 14. Okay. Okay. So, okay, sorry, I'm getting worried about it. I have to go. Oh, okay, sorry. On the left. Okay, cool. So OR. We only lose the R. We're keeping the H, or sorry, the O. I think that should be good.
I got the same thing for
Okay,
15.
thank you. Okay, cool. Cool. So there's that one. Which is also all of them. Wow. Okay. Good job, everybody.
For part G, I'm gonna ask you again about stereochemistry, but would we need to put the like the other, like you see it where the BR is that, you think that's I think it's a chiral center. So would we just put both of the diastereomers for that one? There's two chiral centers.
Yeah, for this one, I think that's what we were talking about a little bit, I think with Chelsea, that since the stereochemistry isn't shown here, you don't have to put like plus enantiomer, right?
Yeah, I'm not sure for this kind of problem. Like, I'm kind of thinking maybe we would have to write the wedge and dash for the BR and the methyl, and then the diastereomer for that one.
Yeah.
And like the methyl would stay the same. But I'm not sure on like that for that like if we would give an enantiomer for that.
Yeah, let me double check. I'm kind of thinking no, since like you just like, she's not telling you to wait, let me double check.
Because they're not defined, but
so it's like that.
But then they have that one methyl that has the dash. So I'm like, so would we?
Yeah, because technically, like you would have this one and like the other one.
And then it would be wedge, but only those would change, not the methyl by itself.
Yeah.
I would think.
Yeah, I'm trying to see maybe.
I don't know. I'm not sure about that.
Any of the past exams. Let me see. Options. Not that one. Okay. Yeah, I'm thinking that just based on like her grading, I'm sure we've had like a reaction like that. I'm trying to find it. Dang. Oh, well, I mean, so this is I just saw this on exam 2. It's asking you to provide the complete mechanism for the reaction. It's just like another alkene, whatever, with HBr. And then like it's added, however, this would be the BR, whatever. But she doesn't do any wedges or dashes, is what I'm trying to say. So I don't think that you have to at all.
I looked on the practice exam, summer 2024 exam number 2, and then on question 8A, I think we did, it was really similar. It was a hydrohalogenation reaction again, and she did show the enantiomer for it.
Oh, she drew the enantiomer?
Yeah. Or at least
Dang.
I
Did
have
she,
for the practice exam too.
was that like the answer? Huh, okay.
I'm pretty sure I went to office hours for that one, but yes. So I think you would have
Dang.
to chemistry.
Okay. Okay. Well, yeah, that's cool too. Yeah, because I guess you would have to say plus diastereomer. Maybe. You definitely wouldn't be wrong for doing it. I don't think so. That's cool. I think that would be fine. Wish that we knew more about that. Okay. Oh yeah. But otherwise, that's all of these problems, which are pretty cray. So good job. Okay. We could go on to 16 now. So provide the missing reagents to complete the reaction below. So this is a, derivative. So to get from chlorine to nitrogen or something else. Let's see. I guess I already have this one up here. This is, what kind of reaction is this? I wish I could tell. Is that, oh, actually, this is a hydration, I think. So that's basically saying this, what we have reacting with an OH with whatever R group we're looking to have will replace this chlorine. So I would have HO and then the R group would be this. So that's CH2, CH3. So I believe that might be it for that one. Let me go ahead and try and find it in here. Is that technically an alcohol? That was actually an alcohol, not hydrolysis. Okay. So I believe that one should be good. Okay, and then just so we can see it, over here, if you're looking, we have, yeah, the chlorine bonds with that one. Yeah, and our OR group stays the same. Cool. So yeah. Is that one okay for everyone?
So an alcohol group with a carboxyl derivative turns into an ester.
Yeah.
Okay.
Yeah. So, what is this called? Acid chloride. And then was someone else going to say something?
Oh yeah, sorry, I was just saying I got the same thing.
Oh, cool. Yeah. So now this way, we're going from an acid chloride to an amide. And I don't know how to do that yet. So I don't know if anyone else kind of knows where that might be located, except I think we found it. Okay.
I think if you check 14 point or 14-9, I think there's
cool
something in there.
Cool. Okay, yeah. So for this is 14-9. I'll switch it. Oh, am I still streaming? Why does this look weird? Can you see my screen?
No.
No.
What the heck? Okay. Okay. Okay, cool. So we're going from an acid chloride to an amide. We're just replacing the chlorine. Let me use a different color. So now we're just replacing this chlorine with, oh, actually that's NCH3 2. So for these ones, it's like just rule, we'll need 2 equivalences. So I'll at least put that one down. So I believe they'll just react with whichever excess hydrogen we have. Let's see. Okay, this one's harder for no reason. Thank you. So, because there's no example with like a different group attached to it, just like the hydrogens. So I'm thinking we'll need at least a hydrogen for it to bond to, or sorry, for our chlorine. Oh, I don't know, we have chlorine over here to bond to. And then, I mean, I believe we'll just have our CH3. Again, I'm thinking it'll just be NH, CH3 2. How do people feel about that?
It should be work because in summer 2021, question 19, part E, this is the exact question that she asked.
Oh, okay. Okay, and then did you go over that one with her?
Exactly.
Okay.
I'm
so
not sure about the product because she asked about the product, but exact this, I believe it's work, yeah.
Okay, yeah, I think so too. There was more of this like, oh wait, there's, I didn't know what that was referring to, Kate, when you said it, but there's a practice problem where the reactant on the left is NHCH3. Cool. Okay, yeah, so that one should work. So just, I guess when you're doing the, carboxylic acid derivatives, for this one, yeah, you just know this is NCH3, 2 of them. And you'll need 1 hydrogen also to react with your chlorine.
But if you want to consider 2 steps, the first step, exact the page that you show in the notes. And for the substitute hydrogen with metal, we should use chapter 10, page 4. You can see how we can replace H with R group, hydrogen with hydrogen.
That's crazy.
If we have to, if we have to use one more one step, I believe we should go with this.
Yeah. Yes. So you could also, I guess, yeah. So hypothetically, another first step would be reacting with 2 NH3, I believe, and then that would give you like NH here and NH here. And then, yeah, you could do a reaction like this. I guess it would be, step 2 would be, our group would be CH3. Oh, but then I don't know how it would work with like, because we'll need it to react on both sides. Oh, I guess you have to go through 2 rounds of it. Yeah.
Yes.
Yeah. So you'll have like leftover of this reactant, I guess.
In the notes explain this process can repeat until there are no more hydrogen.
Yeah. Yes, exactly. That's amazing. I can nearly fully wrap my head around it, but yeah, with like a scale, I guess. I think there might be like a little bit more to it, but I don't know if I really want to go into it right now. But yeah, it's definitely another way to go about it. That's very cool. Oh, Sean, you're doing so well recently. Okay. So yeah, but otherwise, yeah, this the one in red is like a lot of what we saw in the homework for that one. So yeah, I could do either. Where am I going? No. Okay. So yeah. There's those ones. Okay. So yeah. Any other questions for those? Okay. Cool. So 17, find the missing starting material. Drawing the specific compound. Okay. I probably don't know, but first I'd just like identify what it is. So we have an alcohol. That's pretty much all I have. And it's gonna produce a ester and a carboxylic acid. Okay. Bye. Good luck to people leaving. Okay. So missing starting material. I don't know if anyone has an idea of where to find this. I'm sure it's also like in this one somewhere.
It would be in chapter 14, in the reactions with alcohol section. And I got that it was an anhydride because the products were an ester and a carboxylic acid.
Okay, let me find it. Okay, wait, so this one's hydrolysis. Sorry, did you say which page or it's this one maybe?
Well, I'm not sure which page, but oh yeah, that table.
Oh, okay. Oh, okay, cool. Perfect. Okay. So yeah, I definitely have all these tables in my notes and I can put that in the Discord also. Yeah, so exactly. So this is an ester and an a carboxylic acid. Cool. So our thing is in anhydride. So let's see. Maybe we could get a full view of it. Because I would have to kind of understand how it's gonna react with it. Let me see.
What I did was for the
Mhm.
ester, the OR group, I circled that, and then the carboxylic acid, the H, I circled that, and basically that's the alcohol that it came from, and then you just stick the oxygen like onto the ester, or the oxygen from the carboxylic acid onto the ester, and then that's what my starting material looks like.
Oh my god! Wait, what does it look like? Wait,
Yeah.
let me see.
So it's basically like that, but you just remove the part that I circled, and then you
Oh, okay.
together.
Oh, and then add. Here, wait, let me see. I'm not sure if I'll get it all the way. Should probably review those personally. Okay, so at least that, and you said we're removing that other part, but for an anhydride, we'll have to go up again, right? And then another ketone or whatever.
Yeah, except there should be an O in between the
Oh, okay.
yeah, right there. And then like for these, if you're unsure, which I was a little unsure at first when I wrote this, I just worked through the process like from the like I just started with the anhydride and made sure that I got the right products based on the notes.
Yeah. Okay, so let's see, I guess so. Anhydrates, I guess it's easier to go from here. Because it'll react with this. Right. And then that will form the carboxylic acid part. Okay, this one's confusing. I think I might have circled it wrong actually. So on this side, I think that the oxygen is included also.
Yeah, it would be
Okay,
also
okay. Cool. So all of this reacts with the hydrogen. Okay, so yeah. we're kind of working backwards, but yeah, we could go over it again, like through your notes. So this will react with this hydrogen, and then the OR group is just going to attach to form a different one. So that'll be our, yeah, carboxylic acid over here. And then this will attach over here. Yes, exactly. Cool. Okay. Is that okay with people? I think definitely just like go over this like mechanism, or not really mechanism, but just literally like however it pairs with everything. Okay. Sorry, I'm trying to figure out something right now. Oh, okay, wait. I think I'm missing just actually, yeah. I think this will go up at the end also, right? For that part.
Yeah.
Cool. Okay, cool. Okay. So then if no one has like questions, but then I'll go on. Okay. Oh, and then let me just label this. Okay. Cool. So there's that. Okay. Go on to 19. Provide a whole entire mechanism for this. Okay. Let's see. So that's gross. So that's like an I forgot what they're called when this is like an ester with like the Na attached to it. Let's see. Oh, carboxylate anion.
I'm not sure if what I did is right, but how I did it was I just did it like an SN2 reaction. So I went through the whole process of figuring out how it's SN2, and then I just wrote the mechanism for that. And that's what she did with sours. So.
Oh, okay, cool. Okay. So then you identified this as a, yeah, okay, so a strong base.
Yes.
Strong.
Sorry.
Okay, secondary carbon. Yeah. I guess you could just like look at this one and notice it. Oh, and also definitely remember, I'll definitely forget at some point, but SN2 inversion of stereochemistry. So that's what happened when it turned into a dash over there. So yeah, so provide the complete reaction mechanism. So SN2, I have like little sticky notes over here. So I'll put the steps. So nucleophile attacks electrophile. Okay, and then the leaving group leaves. Yes, that's it. And that's like the backside attack. Whoops. Okay. So for this one, the nucleophile attacks the electrophile. Now I'm trying to figure out where my nucleophile is. Honestly, that makes me. Nope. I'll think too long.
The sodium has the positive charge, and then the oxygen is the negative charge. And the oxygen that's ionically bond to the sodium will attack the carbon.
Okay, yeah. Nucleophile. Put the negative sign with it. Okay, cool. So, let's see. So I guess we'll redraw it. Do we have to? the nucleophile, attacks the electrophile, and the leaving group left. That's literally it. Oh, how did you show the sodium like being kicked off?
You don't really need to draw arrows for that, but if you want to keep track of where it goes, technically it would bind with the negative chlorine that gets kicked off from the leaving.
Oh, true. Okay, that's true. But did you happen to just start it like this? Because I think you could also just do that.
But yeah,
Or
yeah.
you had. Okay. All right. Cool. So yeah, I'll just draw like the same thing down here. Okay. Cool. Great ideas. Okay. Cool. There's that one. Oh God. So we could go to 20, then provide the complete mechanism for this one. I really don't want to. Oh, okay, but this is phenyl. That makes sense now. And this one is an ester. And this is also a Grignard, or whatever, reagent. So we could find that in the notes a little bit.
I already kind of did this one, but I found it on page 1411. I can send a picture in the Discord if you want to look at it.
Oh yeah, cool. I have it right here too. So yeah, cool. Okay, so for the Grignard reagent, okay, so it says that our nucleophile will be our group. So what's this? Let me see. I'm wondering if like I want to draw it out. I guess like you kind of have to, right? I would think that would be necessary to show all the electrons. Let's see, maybe this is fine. So yeah, so we have this one reacting with that. So the bond from our R group attacks the carbon right there. So draw it up there. Okay. And then I'll draw the lone pairs on here too. So then that would mean that this one gets kicked off. So that's like our first part of it. So 2, 1. Okay. Okay, so now we have this one.
So what exactly just happened in that step? I'm not very good at pictures.
Yeah, sorry, I'm looking exactly at this. So it just shows you that the bond from the R group, like with the magnesium, comes off, and it acts as the electrophile and attacks the carbon, which is that carbon right there, and then that one breaks off, or the double bond, pi bond breaks off, and it forms another lone pair right there. So that's what we got out of it. And actually the MgBr attaches right here for a second.
Okay.
Yeah, I know. So for these ones, I'm definitely just gonna be staring at the mechanisms. Yeah, so there's that. And apparently this is a good leaving group. We're gonna have, oh, which is not normal. Also, I guess. So this one is now step 2. So I guess straight up just staring at this thing, whatever. Okay, this one leaves. Let me see. Oh, I'm sorry. And then I need to draw in the R group that we gained, which is, I'm just gonna put PHCH2. Yeah. So we have that. Let's see. So according to this, now our product will be 1, 2, 3, 4. Actually, not the last one. Sorry, I'm hurting my own brain right now. Let me see. Okay. Okay. I have this double bond again. Okay. Yeah, that plus the group that left. Oh, whatever that, which is also CH3, CH2. Minus and MgBr. Okay. Oh my god. Okay, 2 more steps. So then, yes. So then it reacts again with the nucleophile we have. See if you guys need a quick look at mechanisms during the exam. Recommend going to key reactions of the chapter. Cool. Yeah. So yeah, that's step 2. So now do step 3. So it's going to be with the same H. Oh wait. PH CH2 MgBr plus this one. So that's why you have 2 equivalents of it. Sorry, this one sucks. Okay. I'll put it in here. Okay. So nucleophilic attack again. So that would mean it's going to be attacking the central carbon again. And then this one's gonna come off. That's what it always does. This is so much. I don't know why she's doing this, but that will result in the product. Okay. And okay, so that's our product. And then step 4, which is the last step for proton transfer. Okay, so, oh, sorry. And then, again, I'm trying to not attach the R group. Let me see. So I'll just have here PHCH2. Oh my god. Okay. I guess. I'm just gonna write it on here. Okay. So this is proton transfer, and now it's going to be an alcohol. And that's our product, I guess. Oh my god. Sorry, that's so ugly and terrible. I guess I had a lot of other room to write. Okay. Bye for those leaving. And yeah, let me. Oh, I thought you would have a quicker way to look at this, but I guess not. It's okay. Okay, is that okay? Sorry, that's very tedious. Bye, Ellie. Thank you. You have a great holiday also, and great rest of your finals. Okay. Okay, so then otherwise we could go on to, I think this is gonna be, yeah, this is the last one for this one. So this one's a terminal alkyne. So I know that needs to react with something else before we can use it. Okay. So nope. So first we have to deprotonate it in order for it to like react with anything else. And again, that's from me looking at the Quizlet that I share. So that's going to be with Na NH2. I'll write it down here. You can see what's happening. So that just means that we lost the hydrogen on here. So now we have a lone pair. And next, let's see. Uh-oh. No, for deprotonation, this is what it looks like. It is kind of tripping me out on how it reacts with the Grignard reagent we're gonna use. Kind of scared. Hold on, give me 1 second.
I didn't use a Grignard reagent for it. I can't speak. Sorry, I have a routine.
No, that's
So I did the same thing you did, and so that goes from an alkyne to an acetylide ion, and so that has a negative charge on it. And then the thing I used was Br CH2CH3.
yes, that's what I meant. Yeah, nearly. Just
Yeah,
has
I know. I
negative
thought
too.
it was for a second.
Okay. Okay, so yeah, so these are added or additional. So we know we'll use it, yeah, for the second one. So CH2CH3. Cool. So yeah, that'll just.
Can you explain the addition of the halogen?
I'm sorry, what was that?
Why was Br added?
Yeah, so that one, let me see if I can find it in those notes. It'll be a chapter 5. That's what you can do to a terminal alkene to add additional like carbon bonds or whatever. It's honestly a little bit hard to understand. Let's see.
Example on the top of page 15 of chapter 5.
Oh, okay.
Yeah. Are you gonna share your screen?
Do you think we need one more step?
One more what?
One more step. We need one more step.
I don't know what the last word you
For
were saying.
the change to trans, because it's a trans, I think.
Oh, let's.
We need NaNH3.
Oh,
my third step, yeah.
Okay, wait, here, give me 1 second. So terminal alkene. Okay, wait, and then yes, so NaNH2 allows the terminal alkene to be deprotonated. Or sorry, terminal alkyne also, just because the 3 bonds. But yeah, so I'm sorry, let me work through this really quick. So yes, we did that first, and you add a nucleophile with a leaving group. So yeah, this is a reaction that's kind of taking place when we do it. So we actually, oh fuck, is it? Let me see. I don't know why this is already attached with the Na right there. Let's see. I guess this one's a little bit easier to tell what's happening. The lone pairs attack like this last carbon that the bromine is on, and then the bromine gets kicked off. Oh, okay. And then I'm sorry. So at first I thought that was that's why I was getting very confused. I was like, how is this changing? So now we'll have this. And now with the correct amounts, I guess we'll just do it going straight first. Okay. Okay. Okay, I'm lost from here for now. So how to reduce this? Someone who already did it. Okay.
NaNH3.
Oh, okay. NaN. Oh wait. Is that?
We change it to the alkane and transfer position.
Cool. Okay, so I got kicked out of the whole entire meeting. So I'm gonna join again right now. Okay. Okay, cool. Anyways. So yes, what I was trying to say, it's probably just like dual screen killing everything. Okay. So yeah, our third step was turning the alkyne into a trans alkene. Yeah, trans. And we know that we use Na and NH3 to do that. Okay. Is that one cool for everyone? Okay. Everyone can see now, right?
Yep.
Okay, cool.
Yes.
Yes.
So then that's it for this first exam. We could go on to the next one. Maybe, hopefully it'll possibly be faster, since we've gone through one at least. So we can try that out, whoever wants to stay. So yeah, let's see. Okay. So we'll do,
Oh, sorry. Oh, if you haven't already like worked through it all, I worked through most of it, but there are like a few questions I have. If you want, I can send you like my work for it if it helps it go faster. But
oh, okay. Yeah, cool. Or actually, also, yeah, I can upload both of them with everything on it. Also, if maybe instead you could just speak up perhaps if I'm struggling. Yeah. Okay, cool. So the first one we're expected to be able to do is number 2. So draw S3 methyl hex in all 3 all. So for this one, I'd definitely start with the parent chain. So hexane, no double bonds. So 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. Yep. Okay. So we have that. And then on our third one, we have, well, actually just kidding. On our third one, we'll have both a methyl and an OH group. Yeah, good luck everyone. Okay. So yeah, just because it's notated on 3 alcohol. And also it's in the S configuration, which is counterclockwise, which is not that way, this way. So we have that. So we know that we're going to have to show our stereochemistry. So in order for it to go that way, let's just hypothetically let's put one of these on here. So I would just go in order and then decide which one's the wedge and the dash. This is 1, 2, 3. So this direction already is S. So if we want it to already be going in that direction, we will make this one the wedge so that we can ignore our lowest priority, which is the methyl. And then our methyl will be the dash. Okay. So there's that one. And we got the same thing, everyone agrees.
that.
Okay, cool. Okay, so there's that one. Now we can go to this next one. Label acid, base, conjugate, acid, conjugate, base. So we know that these ones are like a pair, and the one with the additional hydrogen is the acid one. But since it's on this side, it's a conjugate. Conjugate acid. And then over here we have the regular acid. Here, wait, I'll do it with a different color. So that makes this one the base. acid and base. Okay, so cool. So next we're going to determine, using pKa values actually, determine which way the equilibrium will favor. Okay, well then if we're using pKa values, then we have NH3 and we have NCH, yes. So I guess I'll take these down to the very bottom, right? No. Oh, okay, just kidding. It's right here. Okay. So here's our pKa values. Oh, sorry, that's HCN. Makes sense. Now I know where I've seen it. So we have HCN, and we also have NH3, and then pKa, lower pKa means a stronger acid, right?
Yeah.
Okay. Cool. So HCN is the stronger acid, and I'll write it the right way. HCN. Okay. And NH3 is the weak acid. Okay. Cool. Oh, dang it. I'm trying to remember it. This one was, lower means stronger acid. So HCN was like 9.21, I think. And then this one was like 30 something.
It was 38.
Cool. Okay. 38 pK. Cool. So it's our weak acid. And this one's our strong acid. So which side is the equilibrium going to favor?
Left.
Cool. Yeah. Okay. Is that cool? Is that one done? Makes sense. Makes sense. Cool. All right. So number 5, add any missing lone pairs and draw resonance structures. Okay. Hopefully I'm better at this now. So let me go ahead and do this. And then can someone confirm that positive sign is signaling that there's an additional, no, I don't know. Give me 1 second. Or if anyone else can guess or know what the positive is signaling.
We did this one in
Means-
office hours. So if you want, I can go through it for you.
Yeah, sure. Or well, at least here, I kind of do want to know if I can do it now. But since this is positive, that means I would think that would just mean there's less electrons, but I don't even know, because otherwise it would just be 2 hydrogens. But you can't have like an additional hydrogen.
Yeah, it would just mean that 1 hydrogen is missing, so then there would be 3 things bonded to it when there should be 4, so it'd be a positive charge.
Okay, so just 1 hydrogen. And no lone pairs. Okay, so positive charge. Okay, so any resonance structures for this one? I'm gonna put this one on here. If anyone can like guess or might know. Actually, so one of them I'm thinking, pretty sure this one can move over here since there's only 3 things bonded to it. When there could be 4. That one should be 1, right?
That's right.
Okay. And then also you have to make sure you're following like your charge. So that's, let's do this as 1. That would mean, where is our positive charge?
Wouldn't it be the bottom one? Not the bottom one.
Oh yeah,
Yeah.
cool. Exactly. Cool. So there's that one. Any other ones anyone seen? I'm thinking we can also do this. Wait, yeah, is that correct? It might not be correct.
Partly, you're gonna go from the structure that you just finished drawing, and then that arrow you drew on the bond would be right.
Oh, okay. Okay. Cool. So you can go like that. Okay. Okay. And that means, where's our positive charge? We already have a hydrogen on here. Anyone know where the the positive charge might be? Am I even right in this? Let me see. Oh, actually, okay. I think positive charge will end up over there. Would you say that is correct?
Yes. Yes.
Okay, cool. So we have 2 resonance structures. Are there more, just so we know?
No, that's all.
Oh, okay. God, I hate resonance structures. I never know when to stop. And then here, wait, let me see if I could, sorry, I kind of want to figure out if I can understand where this one went wrong. Then I would have this over here, nothing here, this one here. Why can't I do that? Does anyone know?
If you're gonna take it from the starting structure and try to put that, like the bond or the double bond on the right, up one, then I think it wouldn't obey the octet rule for that top carbon in the ring.
Here, because this one, oh yeah, oh my god, so true. Okay, so definitely I'm gonna write a note for myself and anyone else. Oh my goodness, I'm gonna write in hydrogens. Consider before at least the ones like, yeah, that you're about to alter the bonds with. Okay, cool, makes sense. Cool, thank you. Okay, so there's that one. I'm skipping these ones. Oh god. Okay, I haven't watched this last video again yet, so utilize the carbohydrate provided to answer each part below. So on the Fisher projection, circle the ultimate carbon. I don't know at all.
You're gonna have to look at it like top down, like for instance, that you see that top carbon, you're just gonna count like each intersection between, I wish I could write on the screen right now, but you have to write between each intersection between the H and OHs. So like, yeah, like that one.
Okay, yeah.
So you see the first carbon at the top, that's 1, and then there's a carbon that's attached to the double O, then the one that's yeah.
Okay, so then the penultimate carbon is which one?
Yeah, so that's 5. So that's 5 carbons right there, which means that you at least ruled out that it's going to be that's going to be pentose at least.
Oh, okay. Oh, okay. True.
Then,
okay, cool.
Since that double bonded O is right there, that means it's a ketone.
Here, wait, give me 1 second. So 5 carbon chain equals pentose. Okay, and then we have this one. That's also reminding me, would this, no, I think we have too many for a, yeah, never mind. We have too many for a carboxylic acid. So
Yeah.
ketone. Okay,
So
so
that
we
would
have a
be,
ketone.
so it'd be a keto pentose, sorry.
Okay, cool. Okay, so keto pentanose. Awesome. Okay. So then, yeah, so we still have the first question, circle the penultimate carbon. I can also look in the notes to see. Let's just go ahead and
I
find the
think the carbon
definitions.
that's like the closest, that I think it's the carbon that's attached to the one of the hydroxides, like that's the farthest away from the top carbon. I don't know if that makes
Oh.
sense.
Okay, here, let's see.
Yeah.
So penultimate carbon is
Yeah.
the stereocenter furthest from the carbonyl group. And I keep like not remembering what carbonyl means. Let's go back up. Hello. God, okay. What the frick is a carbonyl group?
It just know that it's talking about the top one. That's
But this
pretty
one, it
much
has the OH one on the bottom, so how would I know?
it. I think it's still
Stereo-
attached to the top. I don't remember that. At least I think that's a different kind of problem though.
Yeah, let's see. So for this one, so is this, does anyone know what the carbonyl group is?
Yeah, that's the top one.
Okay,
And then the like
Okay.
the pentylene, whatever it's called, pentyl whatever carbon is the carbon that's
Mhm.
attached to the hydroxide at the bottom.
Oh.
Not at the bottom layer.
Oh.
Yeah.
Oh, okay,
Like a
sorry.
four-
So
like a four.
again, I haven't really looked at the carbohydrates one much, but so are they always like, these are the same on each end?
That I've seen, yeah.
Okay,
Not that I looked at
Okay.
the assigned practice problems in the textbook, but
okay. Okay. So that'll be our penultimate, and I am gonna go back again just really quick. Let's see. For this from the carbonyl group. So okay, but they're still not labeled on this one. Oh, except it is. Okay, cool. Okay. Dang. Cause, well, never mind. Oh, I think the carbonyl is also referring to this ketone as part of that. So that's why I was kind of confused. Okay, cool. Okay. I'm gonna let my dog in here. Okay. So this next one, okay, determine the maximum number of stereoisomers. So that is 2 to the n equals chiral centers. Okay. So I'm just gonna do this one. That's a chiral center, and that's the only chiral center, right? Yeah, because hypothetically, like if you were trying to look at this one to see if it's a chiral center, it has a hydrogen attached, and then it has like this CH3. But this just means like basically that just means like 2 times this same one. So no, that's why alkenes aren't able to be like chiral.
For this type of problem, I was actually a little confused because in chapter 4, there was something similar we did when we had like the 2 to the n rule, where we could
Mhm.
also do the number of possible easy isomers, and I wasn't sure if like
Oh,
find them. And
yeah.
that alkene is you can do easy with it.
Yeah, so then I wonder if easy counts as a stereoisomer. Let's see if we can find it. Chapter 4.
Yeah, it's on page 5, chapter 4.
Page 5. Okay. Yep, 2 to the n, calculating max possible easy isomers. Then stereoisomer, we get the definition for that. I'm gonna look it up really quick.
Stereoisomers includes diastereomers and enantiomers. On the front page of chapter 6 with the tree chart thing.
Okay, wait, give me 1 second. So first let me interpret this. Okay, wait, 2 to the n for easy possible isomers, which is cis and trans. I think it might be. And n is an easy possible double bond. Okay, so there's that. And then you said chapter 6, and then what page?
The front page. It has like a little tree chart that shows that stereoisomers include enantiomers and diastereomers at the bottom.
Okay, previously isomers are classified as diastereomers. Okay, then same connectivity, different orientation in space. Yeah. Okay, yeah, cool. So easy counts as stereoisomer also. Right. That's the conclusion I'm getting from that, right?
Yeah.
Okay, cool. Hey, okay. So let's see. So then also, anyway, I'll just do that for that one, and then I'll do a new color. So 2 to the n for easy isomers, n equals easy possible double bond. Okay. So, yep, this is, I mean, trans, obviously. So, I'll just circle this as 1. So, I'm thinking that's just going to be 2 to the 1 plus 2 to the 1, which is 4. Cool. Okay. So there's 9. Cool. Yay. Now we get to apply that last thing. Let me see if we can remember it. Whoever is having trouble with it can answer out loud. Let's see. So
Wouldn't it be B? Wouldn't it be B because there's a lot less branching?
Okay, yeah. Okay, wait. First, I wanted to kind of get the rules. Maybe it's just for me, and also more branching. And I think that this has an inverse relationship to boiling point. Is that true?
Yeah.
Okay. Lower boiling point, and then more surface area is, I don't know. Is that more or less?
Less.
I guess that would have to be, oh really? Lower boiling point?
Yeah.
More.
I think it might be also.
I think
You're talking about the length of the carbon chain?
Yeah.
Yeah, it's less. The longer
And
the
more-
carbon chain, the less the less the
Well,
boiling point.
they'll have to be like inversely related.
Yes, I think it's more. So
Okay.
more surface area, more boiling point.
Okay, yeah. So let's just go back to the other exam we're doing. Where did it go? Okay, just so we can copy those rules because we had them. Test review. Nope, wrong one. Okay. 2020. Okay. Longer, yeah.
Right. For when there's a longer carbon chain, it like because like they can fit together better, it allows for more temporary dipole moments, which increases the amount of intermolecular forces.
Yes.
My
Cool. Okay. I was getting so confused with that one. Yeah. Because I was thinking more surface area just meant like, oh, they're able to reach all the bonds, so it's able to break easier. But that is not it at all. So no one remember that, please. Okay, so I'll just paste that right here. Oh, never. Okay. Yeah. Okay, so this one has more branching. Circle the compound with a higher boiling point. This one's the longer carbon chain. Okay.
I have a question.
Mhm.
Less branching means more surface area.
Yeah. Yes, it does.
Oh, okay, thank you. I confused just a second.
Yeah. Cool. Okay, so there's that one. Rank these from less acidic to more acidic. We have figured this one out before. Let's see. This one will be area. Oh, and also, oh my goodness, my cat. Okay. The charges are gonna end up being on different. Actually, no, they aren't. Never mind. Okay. For the conjugate bases, the charges are going to be on the same atoms, right? All of these oxygens. Just so I know. And I'm honestly not too sure if it relates to areo specifically. I think I'll need help because we've literally figured this one out. Is Chelsea still around?
Be the I in areo for induction, because the Br acts as an electron withdrawing group and stabilizes the negative charge.
Okay, cool.
And so the closer the electron withdrawing group is to the negative charge, the better it will stabilize it.
Okay, cool. All right, that's what I was thinking. All right, so this one.
The more stable it is, does that mean the more acidic it is?
Yes, yeah, more stable conjugate base means more acidic parent acid. This
Okay.
one is pulling closer. Let's see. So let's see. So in order, actually, I guess I'll deal with this one later because I'm not too sure. So this one will be less stable. Most stable. And a moderate amount of stable.
I think less stable is D.
You think B is less stable than
No,
A
D.
or oh
D.
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 Oh, okay, yeah. That's why I was like, I didn't want to call this least stable. Okay.
Oh, okay.
Yeah, okay, cool. Because yes, exactly. Because this one only has like hydrogens. So there is no electron withdrawing group. So yeah, least stable. Cool. Okay, beautiful. Okay. Okay, so the most stable is going to be the least acidic, actually. Most stable is the least acidic. So I'll do this as B. Wait, let me make sure I have that right. Do I have that right?
No, D.
Yeah, okay. Okay, let me see. And let me rephrase it. The least stable. Hold on. Least stable conjugate base. Okay. Wait.
Sorry,
probably
I
just
think it's a most stable, least reactive. It has a most or a strong acid.
Yeah, let me see. Okay, wait. So yeah, let's do it in reactivity. So least stable. This one also means it's most reactive.
No,
oh
no,
my gosh, I'm confusing myself.
Most stable, least reactive.
Yeah, that's also true. Yeah. most, I did like the opposite of what you said, so least reactive. And the more stable a conjugate base, the stronger the parent acid. I'm quite sure. And now I'm scared again, so I'm gonna find where I set it on this one, and copy it. If I could find it, let's see.
You passed it.
Oh wait, okay, it's here also. So more stable base, stronger parent acid. Okay. 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 Okay, so the most stable base is B. Okay, cool. And middle, I guess, is C. And then A. And then our least stable is, yeah, because the least stable one would be the most basic, obviously, because it's going to react with everything. All right, cool. D. Okay. Cool. Anything else for that one? Children. Okay. Draw the Newman projection for the most stable conformation of the compound. So most stable is going to be anti conformation. And then let's see. So when you're drawing the Newman projection, let's see. Okay, so we're gonna know it's also the most stable. Oh wait, actually, is it called anti? Maybe not. Whatever. But it is staggered. Don't know how to spell. My cat is being weird. Okay. And then I'm sorry, can someone remind me of what it's actually called to have like these groups be like way apart from each other? It was
yes, in the office hour, he said in the top OH.
Mm-hmm. We could do OH.
And on the bottom, opposite side is BR.
Mm-hmm.
And you know the other thing.
Okay, cool. Yes, and then hydrogens. Yep. Okay. So anti is...
No, sorry, that one's fluorine.
Oh, it is fluorine. Oh, there's also a... Oh.
This is the point of the... No. That one is correct. Yeah.
I see. Okay. BR. And then fluorine. Okay. Okay, cool. And then, sorry, so then what's the opposite of this one called again? The opposite of anti?
Syn.
Okay.
SYN.
Okay. Cool. All right. So there are those. And then I think, let me see if I can double check. Electronegativity. Okay, yeah. Actually, nope, I don't know. I don't want to say something I don't know about. Oh, okay, but Roshan, you said that you did this one in office hours?
Yes, exactly.
Okay, and that's how she did it. Cool. Because I guess I was thinking that the most electronegative atoms are the ones that want to be for this part.
She said the bigger one or the most, yeah.
Okay. Thanks.
Because I think the fluor has more electronegative.
Yeah, it does. That's why I was confused. Okay, cool. Okay, cool, perfect. Awesome. Okay, so there's 12. We could go on to 13. Fill in the missing starting material. So let's see. We have 2 equivalents. So this is going to be one of the, which reaction is it? Let's see. So Grignard reagent with something else. Let me find it first. Okay, not gonna be one of those. The other Grignard reaction, I think. Okay, let me see. Okay. So right now I'm just trying to find that one. If anyone could help it go faster, if anyone knows where it is. I think it's actually chapter 14, but it didn't really look like it. Adds on a alcohol. Oh wait, not 14.
Wait, sorry.
Does anyone?
I just don't
Yeah.
for number 13.
Mm-hmm.
Oh, you're just looking for where we covered it.
Yeah.
I think that was in the chapter on aldehydes and ketones. I got that the material is a ketone, and then it went through a Grignard reaction, and then.
Okay. Yeah. Cool.
In quiz 6, we have same question.
Okay. Let me see. I'm struggling. Aldehydes and ketones is chapter 9, or oh my goodness.
That was chapter 12.
That's what I thought. Maybe that's supposed to be this one. Okay. Is this it? Nope, still no. Interesting. Sorry, I don't know where it went. Okay. And then, so we also have 2 equivalents for these ones.
This would be page 6, and then it tells you that what types of alcohol it produces, and then that's how you would deduce.
Oh yes. Okay, perfect. Okay, so first, that's the best way to go. So we created a tertiary alcohol. So it says if a Grignard reagent reacts with a ketone, it produces a tertiary alcohol. So it's just going to attack, let's see. And CH3, CH2 is just going to be like, I guess, one of these ends, or this one. So let's see. I'm thinking that would just mean we're going to have this same structure. And this is 1, 2. Here, wait, let me do a different color. Okay. 1, 2, 3, 4. Okay, so this one will have the double bond. Oh, 5, 6. Yes, same amount. And I think that will actually be it. Maybe. Let's see. I'm hoping I didn't look at that other one too much. Or this side.
After double bond of oxygen, I think we should have Cl. I'm not sure. I think so.
A Cl in here. Let me see.
Maybe I'm wrong. I'm not sure.
That's it. So it's gonna. Do I have any other notes on this? Not really. Okay. So it's saying we have, and here, let's just try it out. So CH2, CH3, MgBr. So it's saying it's going to attack this carbon and this one's going to come off. And then we'll have oh, okay. So then that means that we'll have the same structure. Okay. But now we'll have the CH3, CH2 attached, and this one will get protonated in the end with H3O plus. So yeah, okay. Sorry, did you say you think you did it wrong?
Yeah, I think first one's
Okay.
actually right because it does say 2 equivalences of the Grignard reagent, and so when we'd see that is in chapter 14. So it would have to either come from an ester or an acid chloride. So yeah, a chlorine would work there.
Oh, okay. Wait. Okay, sorry. So a chlorine would work where? Do I need to insert a chlorine?
You would at the carbonyl group, so it would just be a 1, 2, 3, 4, 5 carbon chain, and then in the place of the 5th carbon would be a chlorine, if that makes sense.
Oh,
Sorry.
okay. Oh, Cl.
Or
Like
yeah, just with one less, like without the CH2 in
that?
between.
Okay,
Just like directly. Yeah, it was hard to explain. Sorry.
that's okay. Okay. Cool. Okay, wait. So you're saying that you got it from chapter 14 instead. So let's see. That's
Yeah, they gave an example with an ester, but it works with acid chlorides.
Okay, so we did end up going with it being from chapter 14. Yeah, it was the 2 equivalences. Okay. But either way, I guess it was the same reaction. Oh, actually, no, because that one means it's going to react twice. But that's why we took off that last one. I see. So that we can add 2 of them.
And also we have acids. We have 2 reagents. The second one is acid, and it's because of that, I think this one is better.
Okay, let's see. Okay, I think the mechanism would be a little bit different. The question is, do we want to take time to go through the Grignard mechanism again? It was kind of terrible the first time. Or, I mean, we could also just like make a note of it and go over it on our own. We did do it before. Yeah, I'll just leave it for now, or well, I just won't redo it. But do try and look at it again. Or work it out however you need. And then this one was also part of the Grignard.
There's a reaction in the book. It's like under key reaction. It says reaction of an ester with the Grignard reagent. I think it just is an ester because I'm looking at this one and it looks identical.
Oh, okay. With an ester?
Yeah, so it would just be, instead of like that Cl bond right there, it would be an O with a methyl.
An O with the methyl. Okay, let's see.
Yeah.
So that would be the same thing as this one, basically. I think that they do actually, I think they work. Oh, that's the thing about them, is that they work the exact same way, I think. So
Yeah.
I think you could do literally either if you want.
Okay, yeah.
Yeah.
Okay, cool.
But it doesn't have acids as a reagent, right?
Oh.
But we have here.
Oh, okay. So let's see. So esters versus chlorides, they can both react with a Grignard reagent. The difference is that chlorides have a good leaving group. So So I'm trying to read it. The product.
This is tertiary alcohol.
Yeah. Nice. So are you saying you don't think it'll work with
we
the?
have to, yeah, it's work maybe. What's the page 14, 12?
The one I'm on, or
Yes, this is chapter 14, right?
yes. Yeah. Yeah, we could try that one. Think on our own and like mess with it a little bit more. They do just take a little bit more time. And it's already pretty late, so I'll just go on to the next one for now. But yeah. Okay. So for this one, fill in the missing starting material by drawing the specific compound that would complete the reaction. So
Whatever it would be, it would have to be a terminal alkene, because didn't we just use both of those in the last time problem that we had something like this?
yeah, exactly. So yeah, this is exactly what you do to get from a terminal alkene to just like a not terminal alkene, whatever that is called, I forgot. So the CH2, CH3 is going to be this one, CH2, CH3. So we can basically just go backwards from there. We'll take it off first. So we'll just have like this part. So we'll have this. That's basically from the second one. And the only thing that happens with this is it deprotonates, or it actually protonates. So no. Sorry. This deprotonates. So if we had just come back from this second step, we would have this one with a lone pair and a charge. But now we're taking that one off too. So we'll just have this terminal alkene or alkyne. Sorry. Okay, that one cool. Okay. Okay. For this one, circle the more reactive acid and briefly explain why. This is a great question. And then hypothetically, we'd have this one's negative, and so is this one if it were that. I don't think area applies really. Oh, just kidding. I always say that. So yeah, whenever you're looking for more or less reactive of an acid, you go through area. So atom doesn't apply. That would mean that the charges on different atoms, they're on the same ones, and resonance will apply with the with the double bond usually. I guess it depends where it is in relation to your like negative charge. So we have this, so let's see. The question of where it would actually be. Okay, wait, I'm just gonna go ahead. Wait, our resonance is more stable. Yes. Base. So let me write that down. Resonance. Okay. And then at that point, for full credit, use appropriate drawings. So I think you would kind of maybe want to show that there's a resonance structure, or at least this. I don't think she would mark you wrong. I was wanting to try out a resonance structure. So I am thinking to create one. I'd have a double bond move here, And then I would move this to a lone pair on this next one. And then I believe that would change the position of the negative charge. Just hypothetically. I don't know if anyone wants to confirm or deny. But yeah, I mean, it's definitely resonance for the answer.
I think that looks right, yeah.
Okay, cool, thanks. Cool. All right, so yeah, for resonance structures, and I'll leave it there and if it's all good. Okay, there's that one. Oh my God, we have to do these again. Okay, SN1, SN2, E1 or E2. So first of all, well, this one's a poor leaving group. And it's only turned into a good one with like HCl or any other thing like that. And I think that's it. I don't know about like H2O or anything. Actually, or one of these. I'm not sure now. Can this one be protonated with this? I think it actually could be. I would think so.
The first one, A?
Yeah, I'm
It's
wondering
no
if.
reaction.
Okay. Did you happen to check that one with her?
Yes,
Okay.
I think so.
Oh, okay, yeah. Because I was wondering, because I was saying that HCl, like I know you definitely can use that because it'll do an acid-base reaction. And this one will grab this and then it'll become H2O and then it can leave. So then I was wondering if it can do that with this one also. But I think, I think that was on our latest exam. I'm gonna look for that really quick.
I think it's a base. Reagent is a base and it's not work with the OH.
Yeah,
I'm
it is.
not sure. I think so.
Yeah, it definitely is a weak base.
For
That's
the
okay.
Winchester reactions, they don't only protonate the leaving group if it's a strong acid.
Oh, okay, cool. Thank you. Okay, cool. So I'll write that over here. Cool. Perfect. Okay, so no reaction. For this next one. Let's go all the way over here. So this one is a good leaving group. This is a tertiary carbon, and this is a weak nucleophile or base, whatever you want to call it. And since it's tertiary, I'm gonna need to go to the
SN1?
Yeah, I believe so, but I do just need it for myself. Let me see. I'll need key things. Okay. Because I always forget which ones are able to happen at each level. So no SN1 for primary or methyl. Okay. And then just no SN2 for tertiary. Okay. But yeah, you can refer to your notes as you need them. So yeah, SN1. Perfect. Okay. This one is strong, bulky base. But this is a methyl. And you definitely can't do E2, which is normally what it is with a methyl.
Guaranteed SN2 when you use that with a bulky base.
Yeah, exactly. Okay, so SN2 you said?
Yeah.
Okay. Okay, yeah, and I'll just write. Okay, cool. All right, there's that one. Now we have this last one. I would say this is a strong nucleophile or base. And this is a primary carbon. So trying to remember, but I simply can't. For primary carbons, anything can happen. For primary, E2, it says it's just main reaction with strong bulky base. Is that the only thing that can happen for primary with E2?
It's primary and strong nucleophile.
Yeah, I also thought it was a strong base. Yeah, so I guess this is saying that I want to confirm that.
What about SN2?
Yeah, I'm sorry. So yeah, so I'm sure it goes through SN2, but this is just making me wonder, does anyone remember like this being the rule? Primary carbons only do E2 with strong bulky bases?
Yes, but it's not right.
No, that might be right. I just don't remember it. Here, so I'll do SN2. And I'll look for it really quick. Let's just see. Okay. Oh God, I don't know where it'll be. Okay, I don't know. It doesn't really say that specifically too much. Otherwise, but that is fine. All right, I'll just leave that the way it is. Sorry. Anyway, so yeah, that'll go through SN2 because it's strong either way. Yeah. So go to the next one. Okay, determine relationships. Oh my goodness. Let's see. CH3, CH2, CH2. I don't have another CH2. Here, let's just count the carbons. So that's gonna be 1. I'll just add them in a second. 1 plus 2, 3, 4, 5, 6, 7. Okay, 7 carbons. Let's see if we have that. 1, 2, 3, 4, 5. Dang it, 6, 7. Okay. See. Okay. So I'm thinking this one is, well, I'm thinking they're unrelated because this should just be a lone carbon. A, you think? Let's see. Different connectivity, I think, would also give you the same thing. So let's try and draw it. So CH3, that's 1 CH2, CH2, CH2. And then it's saying there's a CH, which means there would be like 3 things attached here. Uh-oh. Well, now it looks the same. CH3 times 2, though. Oh, God, I'm confused. So it could also be A, maybe. I don't know if anyone else has any idea on how to figure this out.
Number 2 at the end, it has 2 CH3, right?
Yeah.
then it's not the same as 1 in this structure.
Okay. Okay, cool. That's what I was thinking, but then you said maybe 1 or A for constitutional isomers. And I thought maybe because also this one should just be a lone carbon that it doesn't have. And also it's missing a CH3, which is true.
I think they're unrelated.
All right. I'll just go with that for now. All right. Yellow. Okay. Unrelated.
But both the formulas number of carbon and hydrogen same, right?
Yeah, I think that is.
Then it's isomers.
Yeah, right. Okay, here, let's recount.
I'm not sure. I think.
Does the same number of carbons guarantee that it has some relation to each other though?
I think it does actually. Let me see. Where was chirality? I think that's 6, maybe. Yeah. Okay. Isomers, different compounds have the same molecular formula. Versus, let's see. Oh, it doesn't give me unrelated. Let me go down here. I think that is true. Whether they have, okay, yeah. So do they have the same molecular formula? So let's just find that out. So this one has 7 carbons. And then hydrogens. That's it. So hydrogens, we have 3, 3, 3. No hydrogens there. 2, 2, and 3. Okay. So 3, 6, 9, 12, 13, 14, 15, 16. Okay. And then this one, 3, 6, 9, 10, 6, 6. Oh, wait. 3, 6, 9, 12, 15, 16. Okay. Okay. That was a good way to do it. So yes, they have the same molecular formula. So they're constitutional isomers then. And then did everyone like see the rule for that and everything?
Yep.
All right, cool. Okay. So then the next 2, 3, and 4. This one I think is going to be a chair flip, so I'm just going to number it. However, then we have to keep numbering it that way. I'll go this way. 4, 5, 6, and then 1, 2, 3, 4, 5, and 6. So they're all connected on the same ones. And then I would check for the rules. Up stays up. So let's see here. OH up stays up, and it goes from equatorial to axial. BR stays up, axial to equatorial. F stays down, equatorial to axial. So those ones should be the same compound. I would think. Here, wait, let me double check. Because I know we were talking about hypothetically, like them being equatorial versus axial, maybe changing things in terms of like diastereomers, but I honestly don't know how that one worked. I don't know if Lupita is still here. I don't think so, actually. Okay, that's cool.
I don't think axial or equatorial actually has an effect. I think it just matters if they're up or down.
Okay, cool. Okay then, yeah. So I'll just write here. Up stays up. Okay, yeah. Okay, so then we'll just go with the same compound. That one. Okay. Oh my God, this other one. Okay, so for this one, we can just go ahead and do RNS for these. That would be the best way to do it. So for this one, we have 1, 2, 3 in priority, and the fourth one is backwards. So this one is S. And then we have this one, priority, we have 1, 2, 3. Nope, just kidding, that was all a lie. Okay, hold on. This one's 1, and then 2, 3, 4. I'll get back for that one. And then this one, 1, 2, 3. I'm going in this direction, which is also counterclockwise. Yes. And then so when 4 is wedged, you go the opposite way, right? Does anyone remember? Or we could also check 1, 2, 3. Okay.
You're right.
So we can. Okay. All right. Sounds good. So I'll just rewrite it S R S. And then, I mean, we can also just see what's happening. Oh, goodness. Wait. Oh, I made that harder than it had to be. You could do it either way. But also, if you remember, enantiomers means that like you could find enantiomers by finding if wedges and dashes have swapped. So you can swap wedges and dashes. You could also swap like the actual atoms on each. And then you could also draw the mirror image. So for this one, these ones swapped. And these ones also swapped. But these ones remain the same.
Diastereomers?
Yeah. Yes. So they're diastereomers. See. And then sorry, I'll go back to 16 after this last one too. Okay. For 7, okay. You're supposed to be looking at it. Let's see. Oh, I wish I had the actual thing. Okay, I believe. Oh, it's the same thing as a. Nope, nearly. Because I'm thinking you can rotate it, kind of. So I'm seeing this one, CH3, OH, and then this one's coming out towards you. So if you kind of turned it over this way a little bit, you'd have Br here and the hydrogen here. Would anyone like confirm that, or
Is there any, sorry, is there any rule that dash going to the right and wedge going to the left? Sorry, dash to the left, wedge to the right?
There's actually something like that for when you're doing. So another thing, okay, I was nearly gonna do it, so we can try it, because dashes going one way and wedges going another coincides with like this way you can find the what's the word, no, oh, what is this one called, the model like this, that one?
A Newman projection?
Yes, the Newman projection. I'm trying to see if it would work that way as well, just for a better way to visualize it. Not necessarily.
For R and S, we should consider BR number 1.
For
or OH, which one?
Oh, I'm sorry. You said for R and S. What was
yes,
that?
if we want to consider R and S, which one is number 1, BR or OH?
Let me go. I actually have a note about that somewhere. Let's see if I can find it. It's a good question. I think it might be based off of. Okay, let's see. Highest priority, please. Nope. Okay. Trying to see where these go. On this. BR is higher priority than CL, which might go by the size. Let's go ahead and
Or
check the notes. I'll go ahead and check in here for RNS. Okay. Assess highest atomic number gets priority. Okay. So atomic number of BR is 35 while O is 8. So the BR will get priority.
thank you.
Okay. But that's a good idea. I think that we could also do R and S for this one, and that will be easier. So this one will be 1, 2, 3. Nope, never mind, because when it's when they're all flat, you can't determine RS. I don't know if there's an easier way to explain this one, honestly, unless you can just kind of like visualize it rotating just like a little bit more, so that if you had the model in your hand, you end up looking straight at the carbon right there. Yeah, let's see.
It's depend on power of your imagination. For me, they are same.
Maybe. I do also have a model. If that might make it easier, let me see if I can just like make one really quick.
Honestly, I might just like hope that she doesn't put something like this on the test, because
Yeah.
I spent a lot of time on this one. And I mean, it's just like without the stereochemistry label at all on the structure on the right, it makes it like, I mean, I think it's impossible, but
Yeah, I know. I definitely wasn't able to do it without the molecular model set. Like I thought I would be able to visualize it, and I was like, nope, not at all. Okay, so I have a model in my hand. Let me just make sure I know how to rotate it. Let me see. Okay. Okay. So then I'll go ahead and turn on my camera. I can't see myself. Can people see me? I turned it on like a different person, I guess. Can people see? Does anyone care?
Yes.
Okay. So then this is the model. This one's the BR. This is the CH3, OH, and hydrogen. So we want the CH3 and the OH are in the same plane as the paper. So it's like you're basically like not even caring about this for like the one on the left. We have BR in front and then hydrogen in the back. And if we look at it straight on right here, it's like you're supposed to be looking like straight through this carbon. Then you have this CH3 at the top, and then this one over here, and then the OH is at the bottom, and then the hydrogen is right here. Sorry if that makes sense. So like I kind of drew on there, you have to like look at it and you have to rotate it a little bit. Just imagine it turning over like that. It's really annoying. I'm sorry. I think I can only visualize it because I have had the molecular models. Sorry. Is that okay? I don't know how else to do it. They're in the same plane, and you look at it like this. So you're just turning it. That's all I have. Anyway. So yeah, that's that one. And they are the same compound. Okay. Yeah, and you know, Rashawn, you were saying thinking about them going to like the left or right. I think you definitely can do that. This one. It just depends on like how you decide you want to turn it. I'm sorry. This is very annoying.
No,
That's right.
you are good. Thank you.
This one goes to the right.
I'm not good in this part. I prefer skip this question.
Yeah. Okay. Okay. Anyway, sorry. So provided the missing reagents. Oh my goodness, I'm so tired of doing everything. Let's see. So for this one, we want to go from this alkyne to a trans alkene. So I'm going to go to
I know the right part.
Okay, yeah. So wait, the right part you said. So wait, let me see the difference between these. That's interesting. Okay. So then the first step for this one to get a trans alkene, do you know what it is then?
Yes.
Yeah, what is it?
NaNH3.
Okay, yeah. NaNH3, so that will get us a trans alkene. So this is 1, 2, 3, 4. Yeah, that'll just, oh god, make it like, oh my god, wait. It'll go like this. So now we have a trans alkene, and we want to add bromine to each side.
Yes.
So let's see. Oh yeah, and then you said you already know. So which one would that be?
Bromination. It's the anti-addition.
Okay, and then is that
Br2, CH2 Br2.
here wait, I just have the Br2. Sorry, so it's CH.
Sorry, CH2 Cl2.
Oh, I don't know what that
No,
is.
no.
Wait, find it.
You're right. Br2.
Mhm.
And with, oh yeah, CH2 Cl2.
Oh, okay. I have not been having that one. Okay, so let me go to those reactions really quick so I can find them all.
This is anti-addition.
Okay, cool. Yes. So this one. Oh, okay. See, yeah. So Br2 with CH2 Cl2. Okay, perfect for that one. And then we also, so for the other side, we want it to add through syn addition. So I'm trying to find in my notes where that might be.
First step is same. We should change it to the trans with NaNH3.
Yeah, exactly. But then we wanted in syn addition. I also am not too sure which reaction might give us that. Not sure if anyone else knows. Yeah, it might be okay to leave it for a bit. We could also put it in the Discord if anyone knows this one.
I was stuck on this.
Okay, cool. Okay, sounds good. So otherwise we're not too sure. That's fine. Okay. This one, I don't think we're able to do a, right? Oh shit, maybe we are. Dang.
The answer in chapter 12, page 8.
Okay, for the first one?
Yes, for the first.
Okay. 12, page 8.
She explained only we should check the number of the carbon and also the branch that we have.
Okay, here, let me see. Where we came from. Oh. Let me Just pull them up side by side. Okay. So here, predict the major products. Okay. So that's gonna be, oh yeah, okay. I see. So this is gonna be a ketone reacting with the alcohol. And that'll form a cyclic structure. Let's see. So there's 1, 2, 3, 4, 5. Oh, whoops. Guess we start numbering on the ketone. 1, 2, 3, 4, 5, 6. Okay. So okay, so we will have a 6-ring carbon or whatever. Oh my goodness, here, let me see. So okay, sorry, I'm going directly off of this page. So this one should be our OH group. And then this one over here, 1. Should have a double bond O and another one coming out for that methyl. So then I think we'll lose this pi bond and this hydrogen, and then okay, and then we'll form the full cyclic structure. Oh my god, it's extremely ugly. Sorry. Okay, and that one is protonated as well. God, sorry. Okay, and I just straight up followed this. So I numbered it 1 through 6, and then it ends up that, here, let's see. So this one's gonna rotate all the way around here, form like this whole thing. We still have the methyl over here. That's right here. And then we lose our hydrogen on here. And then we form the bond with the oxygen. Or well, with the carbon attached to the oxygen. And then we protonate it, I guess. I'm also very sorry about that one because I am straight up just copying the mechanism as I see it. Not too sure how to explain it better because I am barely good with it myself. Okay, and then we can also kind of see it here. We had a ketone react with our alcohol. And so the oxygen from the alcohol ends up bonding with the carbon, central carbon, as we see from the ketone. Sorry. I can't explain it much better.
You are great.
Yeah. Okay. So yeah, there's that one. Okay. This next one, NaBH4. I'm definitely going to go to chapter 14 for the other reduction reactions that work. Yeah. If anyone knows where the reduction reactions are in here, definitely somewhere.
I think there was a summary at the end of the chapter 13 notes.
Maybe, let's see. Carboxylic acids. Well, okay, so because first of all, we did this on the last one. This one will reduce ketones and aldehydes, but not carboxylic acids, but we don't have any. So it will reduce this ketone at least to an OH group instead. So I'll just draw that. But I know it also does react with the carboxylic derivatives or what?
Yeah, there was a part in the notes talking about that, but I think with carboxylic derivatives, you can only use the Li or like the lithium aluminum hydride or whatever.
Yeah, I think it depends. I think one of them said that you're able to use NaOH, but I don't know which one it was, so that's why. Dang. Oh, here it is. Awesome. Okay. Okay, wait. Esters react too slowly with NADH, so it selectively reduces aldehydes and ketones. Okay, cool. Perfect. Yeah, they do not do anything with it though. Awesome. And I feel like I saw in the one where this was introduced with the aldehydes and ketones that it also might reduce the alkene. Did anyone else get that? Because it was said and then it wasn't used, I don't think.
I don't think it can do the alkene
Okay.
either. Like on the summary thing, she didn't list it under the like part.
Oh, okay. Yeah. Okay, cool. Yeah, I pretty misread it somewhere. Okay, cool. There's that one. Now we have an amine, no, amine, just a regular amine. So this one is not amines. So that's going to be a reaction with an amine to form a water-soluble salt. It doesn't say like excess or anything, so I'm thinking I'll just do it once. Oops. And I guess I'll just draw the mechanism too. And I know Rashawn is super well versed in these. So, okay, so I know that this one's going to attack this one. And then this one's going to come off. And this one will be protonated. Can I just stop there once this is protonated?
I think it should be changed to NH3 positive charge.
Okay,
Yeah,
exactly.
and then there's a NH4 and a chlorine out on the outside.
Okay, let me see. Anyway, I definitely do see, I mean, just like specifically from right here, I see the, wait, I'm gonna have a stroke. Let me see. That's our R group. actually just kidding, I'm looking at the wrong one. Okay, so I see the protonated NH3, but then just like a single Cl right here, but not the NH4. So where are you getting the NH4 from? Because I guess I see it over here. Otherwise.
I remember seeing that somewhere, but it may have been for something else. It was something.
Yeah,
with,
or maybe
it was something with
this.
amides.
Okay, that's cool. Yeah, I think I have seen that with amides actually. I think it is somewhere else. That's cool. All right, sounds good. There's that one. Our next one, H2SO4 and heat, goes from alcohol to an alkene. And I'm gonna check it because I would be scared to get tricked. Yeah. Yep, alcohol to an alkene. So I'll just go ahead and basically lose this, and then this is our alpha, and then these are betas, and we'll go with the more substituted one. So we'll form our double bond between these two. Okay, that's fine. Cool. Okay. There's that one. Okay, now this is a carboxylic acid derivative.
Sorry, can I see the answer?
For which one?
Oh, thank you. Thank you. Okay, thank you.
Okay, so then this is a reaction with, okay, with a amine. So for these ones, our our chlorine is just replaced by the nitrogen, but we're also losing the H. Oh, this is the NH4 you were talking about. Just
yeah.
Cool. So again, it's like I just straight up copied this whole thing. So we'll keep our double bond O, and according to that, we're gonna lose our H, so we'll have N and then CH3 too. And then I guess we'll give ourselves the NH4 and Cl bonds together. Okay. Is that all for that one? The two equivalents is slightly scaring me right now, but I think I did it right.
I think so too.
Okay. All right, cool. So there's that. Now we have this one, Br. This is a strong nucleophile or base, whichever. And this is a primary carbon. Gonna go to my notes. Oh my god. Okay. God damn it. Okay. Give me 1 second. Okay. I'm sorry. Okay. So then this one is on a primary carbon. So it's either SN1 or E2. Apparently E2 is just for strong, bulky bases with primary ones. So it'll go through SN2, so substitution. So we'll have this CH3. Okay. 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 God, this meeting is from. Okay. Good luck for the person who has been gone, I guess.
Remove the ketone oxygen.
Okay.
Chapter 14, page 12.
Cool. Thank you. 14, page 12. Okay. So yeah. Let me see. Okay, this is amide. Okay, yes, I forget. So amides with the reducing agent, simply just like take it off and it turns into hydrogens and H2. Okay, there's that one. Cool. Turns into hydrogens. Awesome. We're nearly done. Okay, 2 more. Okay. Provide a complete mechanism for the reaction, including lone pairs and formal charges. Okay, so this one is HCl with an alkane, nope, alkene. So HCl. You know what? I'm not sure what the mechanism looks like when it.
SN1.
Is it technically? It's not really SN1 because it's going from alkene to an alkane. So this is like, I think this is
Yes, sugar.
halogenation. Yeah. So let me see. We'll go to chapter 5 just to look at how exactly she draws
I
it.
say SN1 because we have a hydride shift.
Oh yeah, I bet we will have
I'm not
that.
sure.
Yeah. So let's go ahead and hold on. Let's find it first. Okay. So yeah, I just wanted to make sure I drew it right. So the double bond just grabs onto the hydrogen and then this one deprotonates. Okay, so then we're left with this with an additional hydrogen on here. Okay. Dang it, hold on. Because let's see. So the hydrogen's gonna add to the side with more hydrogen, so it's gonna add to this side. Okay. And then let me just copy this structure really quick. Okay. Okay. So we have this structure, and I believe so. This one is going to be yes, because we haven't yet added the chlorine to the other side. So, of course, all right, makes sense now. So we have these hydrogens, and I don't think there will be. Yeah, there isn't a hydride shift here. So we still have this chlorine over here. Okay, so then. Okay, so then the lone pairs are just going to bond to our cation. Yeah, I'll scroll to the previous question after. And then that just gets you the final structure. And if, I don't know, just remember to do your hydride shifts if you need to. But in that case, we didn't. And then, yeah, so this previous one is reduction of amide. So you basically just like take off this one and it adds just like hydrogens to each side. Okay. Place that. And this is the last one, finally. Dang it. Okay, so chlorine to a aldehyde. Okay. Oh, okay. I think I remember how to do this now. Okay. Okay. So can anyone like think of ways to like get to an aldehyde just like in general?
We have a good leaving group. If we have a good nucleophile like CH3COO negative, we have a SN2 reaction and the product is the middle one.
Okay. Okay, so then for this
I'm
one,
not sure only.
yeah, so we could do that, but okay, so my goal, I'm thinking, whenever I see like we're going to aldehydes here, and I did this wrong thing group, whatever. So I'm hoping with this one to go to an aldehyde. Let's go back to my notes because I need the reaction. Okay, so I'm gonna go from an alcohol to an aldehyde. So I'm gonna go from a primary alcohol, which is already like kind of where we have it right there, to an aldehyde. So that'll be one of our steps with PCC. Yeah, that'll be just one of them. But first we'll have to turn our chlorine into a OH group. So we can do that by substitution reaction. So I'm thinking one, we could also just use a strong base or nucleophile, NaOH would work, so that our leaving group will leave and then our OH will end up going on there. So after step one, we'll have this with OH. And then we can just go to step two, which will react to form an aldehyde. So that's, I think that is how you get like basically any other kind of like inferior leaving group or substituent to an aldehyde in general, definitely through the OH reactions. Okay, so there's that one. And extra credit, how to get a carbox. Oh, sorry. Okay. I ruined things. No, I didn't ruin it too much. Never mind. It's just not PCC. I kept calling it an aldehyde, but that's a carboxylic acid. So we're gonna use H2CrO4 instead. Okay.
Wait, wouldn't the alcohol be a secondary alcohol?
Shit. Yes, that is so true. So then, thank you. Can we go from a ketone to a carboxylic acid? Does anyone know? Just move those down. Let's see. This is still true. So dang it. Well, now I'm not sure. because we don't, I was thinking maybe add a Grignard reagent to like elongate it basically, but then we'll just end up having a further away carboxylic acid. I guess I'll just see if I can find it here. Well, shit. Okay, guys. Well, then I don't know about 22.
Neither do I.
Well, that's a great place to end it. But actually, I think that this is going to be the way to go from carboxylic acid to acid chloride. So,
For the second part, you mean extra credit? It's SOCl2.
oh, here, wait. Okay, wait. Do you know where that is in the notes?
I remember. I found it. I don't have right now.
That's okay. Here, let me see. Because I was looking at a different one just now. Let me see if I can find that again.
Because she talked about this recently so much.
Yeah, because otherwise, I mean, like, this is nearly, I mean, it is basically exactly what it's telling us, but I don't know if it's just like each CL would work here, or if it has to be like some other thing as well.
Okay, I found it in the table. Just a second. We have in table about the chapter 8, page 4.
Oh wait, hold on. Here, wait. Someone else found it for you also. They said
there is a
here, if you could see mine, I have it. Someone else said it's on 14, page 10. So yeah, they have the same thing. SOCl2. So that's cool. Okay. SOCl2. Okay. Cool. There's
what about the first part? I'm confused about the first part.
The first one we have not figured out because I don't know anymore. Because I tried to do this one ended up being so this is a secondary alcohol.
Yes, I'm not sure, but the secondary alcohol with in the table chapter 7, page 21, we have example with CH3COO with secondary alcohol. No, it's not. Yeah, it's correct. With
okay.
R2CHX with CH3COO as a weak basis. We have SN2. And SN2, in SN2, we have only one product.
Oh my goodness. Oh my God. I just saw. Okay. I understand what you're saying now. Oh my God. You were right all along. Gosh. Rashawn. Okay, wait. So what Rashawn is saying, react with COOH minus? Or well, I'm sorry. Wait, what was it?
CH3.
Okay.
COO minus.
Okay. Okay. So cool. So that one should just attach and give us another CH3. But then wouldn't that give us?
It's wrong. I think it's wrong.
So because I'm thinking, wouldn't that also give us? That's saying that this will attach CH3 COO minus.
Exactly, it's wrong. We should find another one.
But isn't this one, because I know this is shouldn't it just be COO minus? I think that would work. But are you even able to do that? Because I don't know where, right? So if we were to do that, this is what it would look like, right? It would replace the chlorine with CH3COO minus.
I'm not sure, maybe something with chapter 10 we should.
Or, oh.
I'm not sure. I think about some reactions because.
Yeah, it'd be great if we had an example that's here.
Because it's look like.
I know. We're nearly there. Yes, because COOH. Oh shit, wait, but it would have to be COOH. Or I guess we would need something else after that, or to protonate it. Yeah, I'm not too sure about that one. We could also ask in the chat for that one. Maybe everyone's asleep already. We ended up going very late. Yeah, I'm not too sure about that one.
And which question that we didn't know? We have another question.
Yeah. So is that
18,
one?
Yeah, 18 part.
Yes.
Left side.
Yeah. Okay. Well, yes, those ones we're not too sure. But otherwise, we've gotten through, like, well, actually, literally